3 hours of weirdest objects in space to fall asleep to. Neutrons, stars, and pulsars. Picture a star many times more massive than our sun collapsing under its own gravity. The outer layers are blown away in a supernova explosion, leaving behind a dense core of neutrons, packed tighter than any material found on Earth. This core is the neutron star, an object so extreme that a sugar cube-sized piece of its matter would weigh billions of tons. These stars are no longer powered by nuclear fusion, yet their gravitational force is so immense that it crushes electrons and protons together, creating a solid core of neutrons. Some neutron stars become pulsars. These are rapidly spinning neutron stars with powerful magnetic fields. As the star rotates, charged particles trapped in the magnetic field are flung out at nearly the speed of light. These particles emit intense beams of electromagnetic radiation, often in radio wavelengths, along the star's magnetic poles. If Earth lies in the path of these beams, we see a pulsing signal, much like a lighthouse beam sweeping past a distant observer. This pulsing behavior is what gives pulsars their name. Pulsars are extraordinary for many reasons, but perhaps most intriguing is their uncanny regularity. A millisecond pulsar, for example, can spin hundreds of times per second, and its pulse period can be so stable that it rivals the precision of atomic clocks. Astronomers use pulsars as natural timekeepers to test the general theory of relativity, measure cosmic distances, and even search for elusive gravitational waves. The pulsar's predictable timing has led to breakthroughs, such as confirming the existence of binary systems containing two neutron stars and providing indirect evidence for gravitational wave emission. However, not all pulsars are created equal. Some are young and highly energetic, born out of recent supernova explosions, while others are ancient and have been spun up by accreting material from a binary companion star. These older, faster spinning pulsars are known as millisecond pulsars, and they have become invaluable tools for probing the extreme physics of dense matter and the behavior of space-time itself. Despite their seeming regularity, pulsars occasionally experience glitches, sudden, tiny shifts in rotation speed. These glitches are thought to be caused by changes in the neutron star's crust, or interior, and studying them may help astronomers understand the complex, ultra-dense matter that makes up these stars. In many ways, pulsars are cosmic laboratories. By observing their timing irregularities, electromagnetic emissions, and interaction with nearby stars or planets, astronomers gain insights into the fundamental forces that govern the universe. One particularly interesting class of pulsars lies at the heart of the Crab Nebula, the remnant of a supernova observed in 1054 CE. The Crab pulsar spins at about 50 times per second, and its electromagnetic radiation powers the nebula's glowing filaments. The pulsar's rapid rotation and strong magnetic fields make it an extraordinary particle accelerator, capable of producing extremely high-energy radiation. This radiation illuminates the surrounding nebula, allowing astronomers to study both the pulsar and its environment in unprecedented detail. In addition to their scientific importance, pulsars have captured the public imagination. When the first pulsar was discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish, the signals were so regular that they were jokingly attributed to little green men. While we now understand these signals as natural phenomena, their precise regularity and mysterious origins still inspire wonder. Today, pulsars are key tools in the search for exoplanets, as slight variations in their timing can reveal the gravitational tug of orbiting planets. In fact, the first confirmed exoplanets were found around a pulsar. Pulsars also provide clues about the life cycles of stars. As a massive star evolves, it sheds its outer layers, eventually collapsing into a neutron star. Studying pulsars helps astronomers trace the history of stellar evolution, revealing how matter is recycled through supernova explosions, stellar winds, and compact remnants. By understanding pulsars, we gain a deeper appreciation for the dynamic, interconnected processes that shape the universe. In sum, neutron stars and pulsars are not merely remnants of dead stars. They are vibrant, dynamic objects that shine a light, literally and figuratively, on some of the most fundamental questions in physics and astronomy. From their role as cosmic timekeepers to their status as natural particle accelerators, pulsars provide a glimpse into the universe's most extreme conditions. Through the study of these strange, dense stars, we continue to unravel the mysteries of gravity, matter, and space-time itself. 2. Magnetars. Among the universe's many exotic denizens, magnetars stand out as some of the strangest and most extreme. These highly magnetized neutron stars take the already mind-bending concept of a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons, and add an extraordinary magnetic twist. Magnetars are believed to have magnetic fields 1,000 times stronger than typical neutron stars, making them by far the most magnetic objects known in the universe. To put this in perspective, their magnetic fields are trillions of times stronger than Earth's, capable of distorting atomic structures and creating effects that defy everyday understanding of physics. What sets magnetars apart is not just their magnetic might, but the dramatic ways they behave. Whereas regular neutron stars, including pulsars, generally emit steady pulses of radiation, magnetars are prone to sudden, intense outbursts of energy. These outbursts can include gamma-ray flares and X-ray flashes, which may release as much energy in a fraction of a second as our sun emits in a year. These violent bursts occur when the magnetar's powerful magnetic field twists and deforms its crust, triggering starquakes. These starquakes, in turn, unleash enormous amounts of energy, making magnetars some of the brightest objects in the X-ray and gamma-ray sky. The cause of these super-strong magnetic fields is not fully understood, but astronomers believe it may stem from the magnetar's birth conditions. Magnetars likely form in supernova explosions that produce a rapid, turbulent spin, combined with intense magnetic dynamos. In their infancy, magnetars are thought to spin extremely fast, possibly up to hundreds of times per second. This rapid rotation, paired with the star's collapsing core, could amplify the magnetic field to its extraordinary strength. Over time, the magnetar's spin slows, but its intense magnetic field remains, continuing to influence its environment in profound ways. Because magnetars are rare, they're difficult to study directly. Only around 30 confirmed magnetars are known, compared to the thousands of neutron stars and pulsars that have been catalogued. However, their rarity makes each discovery even more significant. One particularly well-studied magnetar is SGR 180620, which produced a massive gamma-ray flare in 2004 that was so bright it temporarily ionized Earth's upper atmosphere. Even though the magnetar is located tens of thousands of light years away. Events like this demonstrate the incredible reach of these objects and hint at their potential role in shaping the cosmic environment. Magnetars also serve as natural laboratories for studying extreme physics. Their magnetic fields are strong enough to break the usual rules of matter, potentially creating exotic states of matter that can't be reproduced in terrestrial laboratories. Some researchers speculate that within a magnetar's core, matter might exist in forms not seen elsewhere, such as quark-gluon plasmas or other exotic particles. By observing magnetars, Astronomers hope to learn more about how matter behaves under such intense forces and to test the limits of our theories about how particles, forces, and fields interact in extreme environments. Interestingly, magnetars may also be linked to a phenomenon known as soft gamma repeaters, SGRs, and anomalous X-ray pulsars, AXPs. These are sources of intense X-rays and gamma rays that don't behave like typical pulsars or black holes. Over time, evidence is mounted that SGRs and AXPs are in fact magnetars, revealing that the sudden bursts and unusual steady emissions are byproducts of their magnetic field activity. This connection has helped astronomers better understand how magnetars interact with their surroundings and has led to more targeted searches for these elusive objects. While the extreme conditions near a magnetar are uninhabitable, understanding their nature may also have implications for more ordinary environments. For example, the strong magnetic fields of a magnetar might influence nearby gas clouds, star formation regions, or even surrounding planets, should any exist. This raises intriguing questions about the role of magnetars in galactic ecosystems and their influence on the interstellar medium over time. Ultimately, magnetars are a testament to the universe's capacity for producing phenomena far beyond our everyday experience. Their immense magnetic fields, violent outbursts, and the mysterious physics at their cores remind us of the limits of human understanding and the excitement of exploring those limits. As astronomers continue to observe and study these rare, powerful stars, magnetars remain some of the most fascinating and puzzling objects in the cosmos, challenging us to think beyond what we know and inspiring new theories about how the universe works at its most extreme. 3. Black holes, stellar and supermassive. Black holes are perhaps the most mysterious and awe-inspiring objects in the universe. These cosmic enigmas represent a point where nature's laws break down, a region where gravity becomes so intense that not even light can escape. First predicted by Einstein's general theory of relativity, black holes were once thought to be mere theoretical oddities. But today, astronomers have overwhelming evidence that these bizarre objects not only exist, but also play a crucial role in shaping galaxies, regulating star formation, and possibly influencing the structure of the universe itself. There are two main types of black holes that dominate astrophysical research: stellar mass black holes and supermassive black holes. Stellar mass black holes form from the remnants of massive stars. When such a star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. In a cataclysmic supernova explosion, the outer layers of the star are blown away, leaving behind a dense core. If this core is massive enough, typically more than 3 times the mass of the Sun, it collapses into a singularity, a point of infinite density surrounded by an event horizon. Anything crossing this boundary is lost forever, drawn in by the black hole's immense gravitational pull. Supermassive black holes, on the other hand, are found at the centers of galaxies and are millions to billions of times more massive than the Sun. While their exact origins remain unclear, many scientists believe they grew from smaller black holes that formed early in the universe's history, fed by an abundant supply of gas and merging with other black holes over time. These behemoths anchor galaxies, influencing their structure and evolution. In fact, the mass of a galaxy's central supermassive black hole often correlates with the mass of the galaxy's bulge, suggesting a deep connection between black hole growth and the development of galaxies themselves. One of the most fascinating aspects of black holes is the extreme environment they create. The immense gravity near the event horizon warps space and time, causing time to slow down for an observer close to the black hole. This phenomenon, known as time dilation, is not just theoretical. It has been observed through the behavior of light and particles near black holes. Moreover, the accretion disks of gas and dust that spiral into a black hole heat up to millions of degrees, emitting intense X-rays and gamma rays. These energetic emissions allow astronomers to detect black holes indirectly, as the black holes themselves are invisible. In some cases, black holes produce powerful jets of particles and radiation that can extend thousands of light years. These jets, thought to be driven by magnetic fields and the immense rotational energy of the black hole, can impact their host galaxies by heating surrounding gas, regulating star formation, and even pushing material into intergalactic space. The interplay between a supermassive black hole and its host galaxy is a topic of intense study, as it may hold the key to understanding how galaxies evolve over cosmic time. The discovery of gravitational waves has added a new dimension to our understanding of black holes. In 2015, the LIGO Observatory detected the ripples in space-time caused by the merger of two stellar mass black holes. This groundbreaking observation confirmed Einstein's prediction of gravitational waves and opened a new window for studying black holes. By measuring these waves, scientists can learn about the masses, spins, and distances of merging black holes, offering a deeper insight into their population and behavior. Black holes also raise profound questions about the fundamental nature of reality. At the singularity, the known laws of physics no longer apply. General relativity predicts that space-time curves infinitely, but this infinity suggests that our current theories are incomplete. Many physicists hope that studying black holes will help us unify general relativity and quantum mechanics, creating a theory of quantum gravity that could explain what happens inside a black hole and perhaps even what happened at the very beginning of the universe. Despite their reputation as cosmic vacuum cleaners, black holes do not simply consume everything around them. Objects must cross the event horizon to be captured, and most stars, gas clouds, and planets in a galaxy orbit well beyond the reach of the black hole's direct influence. In fact, a supermassive black hole's gravitational effect on a galaxy as a whole is relatively modest compared to the combined gravity of the galaxy's billions of stars. As observational techniques improve, black holes continue to surprise us. The Event Horizon Telescope's 2019 image of the supermassive black hole at the center of the galaxy M87 provided direct visual evidence of a black hole's shadow, a historic achievement that confirmed decades of theoretical predictions. Meanwhile, the discovery of ultramassive black holes, weighing tens of billions of solar masses, challenges current models of how black holes form and grow. In many ways, black holes represent the ultimate frontier of modern physics and astronomy. They are places where the known meets the unknown, where the laws of the universe are pushed to their limits. By studying black holes, we not only learn about these mysterious objects themselves, but also gain insights into the fundamental forces that shape our cosmos. Their sheer mystery and their undeniable impact on the universe make them one of the most compelling topics in all of science. Quasars and active galactic nuclei. Quasars are some of the brightest, most energetic objects in the universe, often outshining their host galaxies. Yet these dazzling light sources are not stars or traditional galaxies, but rather the intensely active cores of certain galaxies. They are powered by supermassive black holes that consume vast amounts of matter, releasing staggering quantities of energy in the process. These distant beacons, first discovered in the 1960s, have since become key tools for understanding the early universe and the role supermassive black holes play in galaxy evolution. The term quasar stands for quasi-stellar radio source, a name that arose when these objects were first detected as strong radio signals from seemingly star-like points of light. Early on, astronomers were puzzled by their extreme luminosity and peculiar spectra. As more observations rolled in, it became clear that quasars are not isolated stars but the active nuclei of galaxies. At the heart of each quasar lies a supermassive black hole, millions or even billions of times more massive than the Sun, surrounded by a swirling accretion disk of gas and dust. As this material spirals inward, it heats up to tremendous temperatures, emitting light across the electromagnetic spectrum. The energy output of a quasar is hard to fathom. A single quasar can emit more radiation than 1 trillion stars combined, making it visible across vast cosmic distances. Some quasars are located billions of light years away, meaning the light we see today left these objects when the universe was much younger. Studying quasars thus provides a glimpse into the distant past, offering clues about how galaxies and black holes formed and evolved in the early universe. One of the most remarkable features of quasars is their variability. Unlike most galaxies or large-scale cosmic structures, quasars can change in brightness over relatively short timescales, sometimes within days or even hours. This variability arises because the regions emitting the light are compact, concentrated near the black hole itself. These changes in luminosity, coupled with detailed spectral observations, have allowed astronomers to learn about the properties of the accretion disk, the black hole's rotation, and the surrounding environment. Quasars are part of a broader class of objects known as active galactic nuclei, AGN. While all quasars are AGN, not all AGN are quasars. Some AGN emit less light, or their light is blocked by dust and gas, making them harder to detect. Others may be oriented such that their powerful jets of particles point directly toward Earth, appearing as blazes. The diversity of AGN types, quasars, blazes, Seyfert galaxies, and radio galaxies reflects the different ways in which supermassive black holes interact with their environments. Quasars also play a significant role in the cosmic ecosystem. As material falls into the central black hole, powerful outflows and jets are often generated. These jets can extend thousands or even millions of light years, pumping energy and matter into the surrounding galaxy and beyond. This process, known as feedback, is thought to regulate star formation in the host galaxy. In some cases, the jets may heat or blow away gas that would otherwise condense into new stars, effectively shutting down further star formation. In other cases, they can compress gas clouds, triggering new star birth. Understanding these feedback mechanisms is key to explaining why some galaxies appear red and dead, while others remain active and vibrant. Quasars also serve as cosmic lighthouses, illuminating the intergalactic medium and providing a way to map the distribution of matter in the universe. When light from a distant quasar passes through intervening gas clouds, the gas leaves telltale absorption lines in the quasar's spectrum. By analyzing these absorption features, astronomers can learn about the composition, density, and movement of the gas between galaxies. This technique has been crucial for studying the large-scale structure of the universe, including the cosmic web of filaments and voids that connects galaxies on the grandest scales. Despite decades of research, many questions about quasars remain. For example, what triggers a galaxy's central black hole to enter this highly active, luminous state? Why do some quasars turn off after a relatively short time, while others remain active for millions of years? How do quasars influence the formation of galaxy clusters and larger cosmic structures? As observational technology improves and more data becomes available, these mysteries are gradually being unraveled, helping to piece together the story of how galaxies, black holes, and the universe itself evolved. In the end, quasars are far more than just incredibly bright points of light. They are dynamic, complex phenomena that connect the small-scale physics of black holes with the large-scale structure of the cosmos. By studying quasars and other AGN, astronomers are uncovering the mechanisms that drive galaxy evolution, the nature of supermassive black holes, and the history of the universe. As a result, these enigmatic objects remain some of the most fascinating and important subjects in modern astrophysics. Rogue planets. Drifting in the vast, dark gulfs between stars are rogue planets, worlds that wander the galaxy without a parent sun. Unlike the planets we're familiar with, which orbit stars and bask in their light, rogue planets are cosmic nomads. They travel through interstellar space, shrouded in darkness, untethered from any stellar system. This isolation sets them apart as some of the strangest objects in the cosmos, raising compelling questions about how planets form, survive, and even thrive in the loneliest corners of the universe. Rogue planets are thought to form in much the same way as regular planets, within the swirling disks of gas and dust that surround young stars. However, at some point during their early history, they are ejected from their home systems. This can happen when a massive object, such as a neighboring planet or a passing star, disturbs their orbit. The resulting gravitational interactions can fling the planet into space, leaving it to roam the galaxy indefinitely. Once free of their parent stars, these planets have no stable source of heat or light, making their detection incredibly challenging. Despite the difficulty of observing rogue planets, astronomers have developed ingenious methods to identify them. One of the most effective techniques involves gravitational microlensing. When a rogue planet passes in front of a distant background star, its gravity acts as a lens, bending and magnifying the starlight. This temporary brightening reveals the presence of the rogue planet, even though it emits no light of its own. By carefully monitoring large regions of the sky, astronomers have been able to detect several candidate rogue planets, confirming that these lonely worlds are far from rare. What makes rogue planets so intriguing is the possibility that some of them may still harbor heat deep within their cores. Planets retain residual heat from their formation, and some generate additional heat through radioactive decay or internal friction. This warmth, though faint compared to a star's energy, could prevent subsurface oceans from freezing solid. If a rogue planet has a thick enough atmosphere or a layer of insulating ice, it might maintain conditions that could, in theory, support microbial life. Such environments would be vastly different from those on Earth, but they open the door to new possibilities for life in the most unexpected places. Another curious aspect of rogue planets is their potential variety. Some may be rocky, Earth-sized worlds, while others could be gas giants with swirling atmospheres. There may even be rogue planets with moons, creating miniature solar systems adrift in space. This diversity reflects the chaotic nature of planet formation and evolution. By studying rogue planets, astronomers gain valuable insights into the processes that shape planetary systems and the forces that can disrupt them. In addition to providing clues about planetary formation, rogue planets challenge our understanding of what makes a world habitable. Traditionally, habitability is associated with a planet's distance from its star, known as the habitable zone, where conditions are right for liquid water to exist on the surface. Rogue planets, however, exist outside these zones altogether. If life can survive on a rogue planet, hidden beneath a thick crust of ice or sustained by geothermal energy, it would demonstrate that habitability isn't solely tied to a star's energy. This realization broadens the scope of the search for extraterrestrial life, encouraging scientists to consider environments far different from those found in our solar system. Rogue planets also have implications for our understanding of galaxy dynamics. Because they are so difficult to detect, the true number of rogue planets is unknown, but estimates suggest there may be billions in the Milky Way alone. These free-floating planets add to the galaxy's mass, influencing its overall structure and gravitational behavior. By studying them, astronomers can refine models of how galaxies evolve and interact on cosmic timescales. In recent years, the discovery of rogue planets has prompted speculation about their role in the history of our own solar system. Could there once have been an extraplanet that was ejected long ago, leaving behind the current arrangement of planets? The idea, while not yet proven, offers a tantalizing possibility that even our solar system might have once hosted a rogue world. As new observational techniques and more sensitive instruments are developed, the study of rogue planets will likely expand. Upcoming missions and telescopes may reveal many more of these wandering worlds, offering deeper insights into their nature, origins, and potential for hosting life. By shedding light on these lonely travelers, astronomers not only uncover more about the planets themselves, but also gain a greater appreciation for the dynamic, ever-changing galaxy we call home. Oumuamua and interstellar visitors. In late 2017, astronomers made a discovery that stunned the scientific community, the first known interstellar object passing through our solar system. Dubbed Oumuamua, Hawaiian for scout or messenger, this strange visitor wasn't a comet or asteroid from within our planetary neighborhood. Instead, it was an entirely alien object from beyond the solar system, traveling at such high velocity that it could never have been gravitationally bound to the sun. What made Oumuamua so intriguing was not just its origin, but its unusual characteristics. Unlike the round or irregular shapes of most asteroids, Oumuamua appeared elongated, somewhat like a cigar or needle, based on how its brightness changed as it rotated. This rapid, tumbling motion, combined with its elongated shape, defied expectations. Equally puzzling was the lack of a visible tail or gas cloud, which comets typically display when they approach the sun and their ices sublimate. Instead, Oumuamua seemed to lack volatile materials entirely, appearing more like a rocky or metallic body. Yet, as it moved away from the sun, it experienced a subtle acceleration, something usually attributed to outgassing in comets, though no such gas was detected. These peculiarities sparked a flurry of debate. Was Oumuamua a shard of a larger body, shattered by a distant star's gravity? Could it be a fragment from an ancient planetesimal ejected during the tumultuous early stages of another solar system's formation? Or, more provocatively, could it be an artificial object, perhaps a relic of alien technology? Some scientists, including Harvard's Avi Loeb, speculated that its unusual acceleration and shape might suggest a light sail or other engineered structure, while the majority of experts lean toward natural explanations. Oumuamua's unique nature has kept the conversation alive. Whatever its origin, Oumuamua's journey is a reminder of how dynamic and interconnected our galaxy truly is. For billions of years, planetary systems have formed, collided, and evolved, ejecting countless fragments into interstellar space. These objects drift for eons, crossing the void between stars, until one day entirely by chance, they pass through a system like ours. Oumuamua's brief visit was a rare opportunity to glimpse this process in action. Although it passed out of the solar system too quickly for a detailed investigation, its detection underscored the importance of monitoring the sky for future interstellar travelers. In fact, another interstellar visitor was discovered in 2019, 2I Borisov. Unlike Oumuamua, Borisov displayed more traditional cometary behavior, with a clear tail and visible outgassing. Its arrival confirmed that objects from other star systems do indeed pass through our solar system from time to time. Unlike Oumuamua's enigmatic appearance, Borisov resembled the comets we're familiar with, yet its interstellar origin was unmistakable due to its trajectory and speed. Together, these two discoveries, Oumuamua and Borisov, marked the beginning of a new era in astronomy, where studying interstellar objects is no longer hypothetical, but a tangible reality. Interstellar visitors offer invaluable clues about the conditions and materials present in other planetary systems. By analyzing their composition, structure, and behavior, scientists can learn about the processes that shaped distant star systems, their chemical makeup, and the forces that ejected these objects into the galaxy. They may also help refine our models of how solar systems evolve over time, shedding light on the chaotic early stages of star and planet formation. Looking ahead, new telescopes and space-based observatories, such as the Vera C. Rubin Observatory, promise to detect more interstellar objects. Improved detection methods mean we may soon find many more examples, allowing for comparative studies and a better understanding of the diversity of these alien fragments. If one of these objects is detected early enough, it may even be possible to send a spacecraft to study it up close, providing a direct sample of material from another star system, something that would revolutionize our understanding of the galaxy's building blocks. Oumuamua and other interstellar visitors remind us that the boundaries of our solar system are not fixed. The galaxy is a vast, interconnected ecosystem where matter is exchanged and shared over immense distances and timescales. By studying these visitors, we glimpse a larger story, the ongoing dynamic exchange of material and information that binds the stars, planets, and systems of the Milky Way into a grand, ever-evolving whole. Exotic exoplanets. When the first confirmed exoplanet, 51 Pegasi b, was discovered in 1995, it shattered many preconceptions about the types of planets that could exist. In the years since, thousands of exoplanets have been found orbiting other stars, and they come in a staggering variety of sizes, compositions, and orbits. Some of these worlds are so strange that they stretch the boundaries of what we thought possible, making them some of the most exotic objects in the universe. One category of exotic exoplanets includes so-called hot Jupiters. These are massive gas giants like Jupiter, but they orbit incredibly close to their host stars, often completing an orbit in just a few days. Such proximity means these planets are baked to extreme temperatures, with their atmospheres expanding and sometimes even being stripped away by stellar radiation. The intense heat can cause their clouds to consist of vaporized metals and other unusual compounds, creating bizarre and alien weather patterns. Some hot Jupiters might experience rains of molten iron or silicates, while others may have winds that reach speeds of thousands of kilometers per hour, redistributing heat from their star-facing sides to their cooler night sides. Then, there are the so-called super-Earths and mini-Neptunes. These planets don't exist in our solar system, but they appear to be among the most common types of planets in the galaxy. Super-Earths are rocky planets larger than Earth, but smaller than Neptune, often with thicker atmospheres and higher surface pressures. Some may have global oceans or thick, hazy atmospheres rich in hydrogen and helium. Mini Neptunes, on the other hand, are gaseous worlds that might have deep, crushing atmospheres or icy cores. These categories suggest a planetary diversity far beyond the rocky, terrestrial worlds and gas giants of our own solar system. Some of the most fascinating exotic exoplanets are those that challenge the very notion of what a habitable planet might be. Take, for instance, lava worlds. These planets are so close to their stars that their surfaces are molten seas of rock. One side may be permanently exposed to the star, with temperatures hot enough to vaporize rock, while the other side remains in perpetual darkness, possibly harboring a thin layer of solidified crust. Understanding these worlds pushes scientists to rethink how planets evolve under extreme conditions. Another category that captures the imagination is water worlds. These planets may have a global ocean hundreds of kilometers deep, with no land masses at all. Such planets challenge our understanding of how atmospheres, oceans, and internal geologies interact. Beneath their deep oceans, some water worlds might have high-pressure ices, or even exotic forms of water that behave differently than the water we know on Earth. These planets raise intriguing possibilities for habitability, as deep oceans could serve as cradles for alien life, protected from harmful stellar radiation. Even more exotic are planets orbiting pulsars. Pulsars are the dense, rapidly rotating remnants of massive stars that emit powerful beams of radiation. Planets around pulsars are exposed to an environment so extreme, bathed in high-energy radiation and intense magnetic fields, that it's difficult to imagine how they formed or survived. Yet a few such planets have been discovered, suggesting that planetary formation may be more robust and versatile than previously thought. And then there are the truly outlandish worlds, planets with atmospheres made of evaporated metals, planets that orbit multiple stars in intricate dance-like patterns, and rogue planets, worlds that have been ejected from their home systems and drift through the galaxy, untethered to any star. Each new discovery adds another piece to the puzzle of planetary diversity and demonstrates that our solar system is just one example among countless possibilities. Exotic exoplanets have fundamentally changed how we view the universe. They've shown us that planets come in an astonishing range of forms, many of which defy traditional classification. Studying these strange worlds not only satisfies our curiosity about the cosmos, but also helps refine our understanding of how planets form, evolve, and interact with their environments. Every new exoplanet discovery is a reminder that the universe is far more varied and complex than we could have imagined, and that the possibilities for planetary systems are, quite literally, endless. Brown dwarfs. Brown dwarfs occupy a curious middle ground between planets and stars, too massive to be considered planets, yet not quite massive enough to sustain the nuclear fusion that powers stars. These failed stars blur the boundaries of celestial classification. Despite their name, brown dwarfs aren't actually brown. In fact, their colors range from deep red to magenta to purple, depending on their atmospheric composition and temperature. They are enigmatic objects that challenge our understanding of how stars and planets form, evolve, and interact. A brown dwarf forms much like a star from a collapsing cloud of gas and dust. However, its mass, typically between 13 and 80 times that of Jupiter, is insufficient to trigger sustained hydrogen fusion. Instead, brown dwarfs derive their energy from gravitational contraction and the fusion of a heavier isotope of hydrogen called deuterium. This limited fusion phase is short-lived. Once the deuterium is used up, a brown dwarf slowly cools and dims over time. Unlike stars, which can shine for billions of years through nuclear fusion, brown dwarfs fade steadily, radiating heat left over from their formation. This cooling process makes brown dwarfs particularly interesting for astronomers. Since they don't maintain a stable energy output like stars, their temperatures and spectral characteristics shift as they age. This variability provides a natural laboratory for studying how atmospheres, clouds, and molecular chemistry evolve under different conditions. Observing brown dwarfs in various stages of cooling gives researchers clues about the processes that might occur on exoplanets, especially those that are gas giant-sized and have complex atmospheric dynamics. One of the remarkable features of brown dwarfs is their highly dynamic and diverse atmospheres. Although they lack the nuclear fusion that powers stars, brown dwarfs can still exhibit surprisingly star-like phenomena, such as flares and auroras. Their atmospheres often host thick layers of clouds composed of exotic materials, like silicon or metal oxides, that aren't found in the atmospheres of most planets or stars. The study of these clouds has helped refine models of atmospheric physics and has informed the search for weather patterns on distant exoplanets. For instance, astronomers have detected turbulent storms on brown dwarfs, with rotating cloud features that resemble the great storms seen on gas giants like Jupiter. Brown dwarfs also serve as valuable benchmarks for understanding the lower mass limits of star formation and the upper mass limits of planetary formation. When do we call an object a very large planet rather than a very small star? Brown dwarfs occupy this transitional category. As such, they provide key insights into the processes that shape not only stars and planets, but also the distributions of these objects within star-forming regions and clusters. Furthermore, brown dwarfs come in a variety of spectral classes similar to stars. The earliest known classes, L and T dwarfs, include objects with cooler temperatures and clouds of metal oxides and sulfides. The more recently discovered Y dwarfs are even cooler, some with temperatures approaching those of Earth's atmosphere, making them among the coldest objects directly observed outside our solar system. These cooler brown dwarfs provide a unique opportunity to study conditions that might resemble those of gas giant exoplanets, or even rogue planets that have cooled for billions of years. In addition to their atmospheric intrigue, brown dwarfs are also significant as potential stepping stones in planetary system formation. Some brown dwarfs have been found with their own disks of gas and dust, hinting that they may form miniature planetary systems. In other cases, brown dwarfs serve as companions to stars, offering astronomers the chance to study how interactions between objects of vastly different masses influence their orbits, rotation rates, and even their physical evolution over time. In recent years, advanced instruments and techniques have allowed astronomers to study brown dwarfs in greater detail. Observatories like the Hubble Space Telescope and the Very Large Telescope have imaged brown dwarfs directly, while surveys using infrared telescopes have identified populations of these objects across the galaxy. These efforts have revealed that brown dwarfs are far more common than once thought, scattered throughout star-forming regions, and even drifting alone through interstellar space. Each new discovery contributes to a more complete understanding of the diversity and distribution of celestial objects. In many ways, brown dwarfs challenge our neat categorization of the cosmos. By existing in the gray area between planets and stars, they remind us that nature often defies our expectations, creating objects that don't fit easily into predefined boxes. As astronomers continue to study these unique objects, brown dwarfs will undoubtedly provide more surprises and deepen our appreciation for the complexity and diversity of the universe. White dwarfs and their peculiarities In the quiet aftermath of a star's long life, a white dwarf emerges, small, dense, and faintly luminous. These stellar remnants represent the end stages of stars like our Sun. After billions of years of fusing hydrogen into helium, and later helium into heavier elements, the star expels its outer layers, creating a glowing planetary nebula. What's left behind is the core, a white dwarf, roughly the size of Earth but with a mass comparable to the Sun. These fascinating objects are among the most stable structures in the cosmos, but their peculiarities make them truly stand out. White dwarfs are incredibly dense. A teaspoon of white dwarf material would weigh several tons. This density arises because the gravity of the leftover stellar core is so strong that electrons are forced into close quarters, creating a state of matter known as degenerate electron gas. This degenerate pressure, rather than ongoing nuclear fusion, supports the white dwarf against further collapse. As a result, the core remains stable, shining faintly as it slowly cools over billions of years. The composition of white dwarfs reveals the final products of a star's nuclear burning. Most white dwarfs are primarily made of carbon and oxygen, the ashes of the helium fusion that occurred in the star's core. Some may also contain helium, or even layers of heavier elements, like neon or magnesium, depending on the mass of the original star and the details of its fusion history. By analyzing the light emitted from these cooling stars, astronomers can reconstruct the life story of the parent star, learning how it processed its nuclear fuel and what elements it contributed to the surrounding interstellar medium. What's particularly intriguing about white dwarfs is their slow but inevitable cooling process. Once formed, they no longer have any internal energy sources. Over time, they radiate away their heat, becoming cooler and dimmer. This cooling sequence provides a cosmic clock, allowing astronomers to estimate the age of the surrounding stellar population. By comparing the temperature and luminosity of a white dwarf to theoretical cooling models, scientists can determine how long it has been since the star completed its main sequence and red giant phases. Despite their seemingly calm nature, white dwarfs occasionally exhibit dramatic behavior. Some white dwarfs exist in binary systems, where they can accrete material from a companion star. If enough material accumulates, the white dwarf can undergo a thermonuclear runaway event, creating a nova. In more extreme cases, if the white dwarf approaches a mass near the Chandrasekhar limit, about 1.4 times the mass of the Sun, it may explode as a type Ia supernova. These supernovae are incredibly important to astrophysics, serving as standard candles for measuring cosmic distances and studying the expansion of the universe. Even isolated white dwarfs can have peculiar traits. Some show evidence of strong magnetic fields, potentially the result of a star's magnetic dynamo being compressed as the core contracts. These magnetic fields can influence the behavior of accreting material and produce unusual emission features. Other white dwarfs exhibit metal-rich atmospheres, a curious phenomenon, given that heavy elements should sink into the star's interior under its strong gravity. The presence of these metals suggests ongoing accretion from surrounding debris disks or the remnants of planets that once orbited the star. These polluted white dwarfs provide clues about the fate of planetary systems and the ultimate end of their host stars. White dwarfs also play a role in the search for exoplanets. Some white dwarfs show evidence of orbiting debris, likely the shattered remains of rocky planets or asteroids. By studying these remnants, astronomers can learn about the composition of planets that existed before the star's demise, giving us a glimpse into the diversity of planetary systems. These observations suggest that planets can survive, at least in part, long after their stars have exhausted their nuclear fuel, hinting at the resilience of planetary material in the face of stellar death. Perhaps the most intriguing aspect of white dwarfs is their eventual fate. Over trillions of years, as the universe continues to age, white dwarfs will cool to the point where they no longer emit visible light. These hypothetical objects, known as black dwarfs, would be dark, cold remnants of stars. However, the universe isn't old enough yet for any black dwarfs to exist. The slow journey from white dwarf to black dwarf serves as a poignant reminder of the vast timescales over which cosmic evolution unfolds. In essence, white dwarfs are not merely the remnants of stars. They are windows into the life cycles of stellar systems, the history of the galaxy, and the future of our universe. Their unique properties and behaviors offer a wealth of information, bridging the gap between the explosive violence of a star's death and the serene, timeless silence of its long cooling phase. The Great Attractor. Among the most mysterious features of our universe's large-scale structure is the Great Attractor. This enormous region of gravitational influence lies roughly 150 million light-years away from Earth, yet its effects are so profound that they seem to pull entire galaxy clusters, ours included, toward it at astonishing speeds. Despite decades of study, the exact nature of the Great Attractor remains elusive. Is it a massive cluster of galaxies, an unusual concentration of dark matter, or something else entirely? The story of the Great Attractor began in the 1970s and 1980s, when astronomers noticed that galaxies in our cosmic neighborhood were not simply expanding outward, as expected from the Big Bang. Instead, they were moving toward a specific point in the sky at a remarkable pace of over 600 kilometers per second. This observation hinted at the presence of a large, unseen mass, a gravitational focal point capable of redirecting the motion of galaxies across hundreds of millions of light years. What makes the Great Attractor especially puzzling is its location in the sky. It resides in a region called the Zone of Avoidance, a part of the sky obscured by the plane of our Milky Way. Dust, gas, and countless stars block our view, making it difficult to see what's actually there. In essence, the Great Attractor is hidden behind a thick cosmic curtain. Astronomers must rely on indirect methods, like tracing the movements of nearby galaxies or using X-ray and radio telescopes that can penetrate the Milky Way's dense foreground to infer its presence and properties. What little we know about the Great Attractor is tantalizing. It appears to be centered around the Norma cluster, a dense region of galaxies that emits a significant amount of X-rays, suggesting that there is not only a large population of galaxies, but also a vast amount of hot gas. The combined gravitational pull of these galaxies, their dark matter halos, and the surrounding intergalactic medium is thought to create the gravitational lump we call the Great Attractor. However, even this impressive mass seems insufficient to fully explain the observed motions of galaxies in its direction. In recent years, astronomers have started to piece together a larger picture of cosmic flow patterns. Beyond the Great Attractor lies the even more massive Shapley supercluster, a vast conglomeration of galaxy clusters that may exert its own gravitational pull. Some researchers suggest that the Great Attractor's apparent influence could be partly due to our local motion toward this larger structure. This interplay of gravity on immense scales highlights how interconnected the universe's largest structures really are. Despite its name, the Great Attractor is not a single, well-defined object. It's more accurately described as a gravitational anomaly, a region of space where the density of matter is higher than average, causing galaxy clusters to converge. This anomaly underscores the complexity of the universe's large-scale structure. Galaxies are not evenly distributed, but are instead found in clusters, filaments, and walls that weave through cosmic voids. The Great Attractor represents a crucial knot in this cosmic web, pulling material inward and helping to shape the vast cosmic network. Understanding the Great Attractor is not just an exercise in mapping the universe, it also provides insights into the mysterious dark matter that makes up most of the universe's mass. If the Great Attractor's gravitational pull cannot be fully accounted for by visible galaxies and gas, it suggests that a significant portion of its mass is dark matter. Studying this region could therefore shed light on the nature of this invisible substance and its role in shaping the cosmos. As new observational technologies come online, astronomers hope to pierce the veil of the zone of avoidance and get a clearer view of the Great Attractor. Upcoming surveys using more sensitive infrared and X-ray telescopes may finally reveal the full extent of the galaxies, gas, and dark matter concentrated there. Meanwhile, ongoing studies of galaxy motion and cosmic flows will help refine our understanding of how massive structures like the Great Attractor influence the universe's expansion and evolution. In many ways, the Great Attractor represents the hidden forces that govern our universe. It's a reminder that even on the largest scales, the cosmos is filled with unseen influences, massive structures, mysterious dark matter, and the intricate dance of gravity. By unraveling the mystery of the Great Attractor, astronomers not only map a crucial piece of the cosmic web, but also deepen our understanding of the universe's most fundamental forces. Cosmic voids and superclusters. The large-scale structure of the universe is anything but uniform. On one end of the spectrum are sprawling superclusters, enormous regions densely packed with galaxies, hot gas, and dark matter. On the other end are cosmic voids, vast expanses where galaxies are few and far between. These contrasting elements of the cosmic web give the universe its strikingly filamentary appearance. Galaxies and clusters linked by long, thin threads of matter, with immense empty regions between them. Together, superclusters and voids reveal the universe's intricate tapestry and help us understand its formation and evolution. Cosmic voids are some of the emptiest places in the universe, spanning tens to hundreds of millions of light years. While not entirely devoid of matter, voids contain far fewer galaxies than average, often only a handful scattered over vast distances. These regions arise because of the way matter clumps under gravity. Over billions of years, slight variations in the density of the early universe grew more pronounced. Dense regions drew in more material, forming galaxies, clusters, and superclusters. Meanwhile, underdense areas, voids, were left behind as matter flowed out toward the denser structures. The result is a universe that looks almost sponge-like on the larger scales, with galaxies clustering along filaments and walls, and voids occupying the spaces in between. At the opposite extreme are the superclusters, vast regions where multiple galaxy clusters group together, forming some of the largest structures in the cosmos. These superclusters contain thousands of galaxies and immense quantities of hot gas that glow in X-rays, as well as a significant amount of dark matter. The Virgo supercluster, which houses our Milky Way, is one such region. Even larger structures, like the Shapley supercluster or the Sloan Great Wall, extend for hundreds of millions of light years and are home to countless galaxies. These superclusters are the nodes of the cosmic web, the hubs where filaments converge. One of the most fascinating aspects of voids and superclusters is the way they reflect the universe's origins and composition. The cosmic web's structure was seeded by tiny quantum fluctuations in the early universe, which were amplified by the rapid expansion during inflation. As the universe cooled and matter began to clump, these initial fluctuations grew into the vast network of voids and filaments we see today. The patterns of these structures offer a glimpse into the universe's earliest moments, allowing scientists to test theories of cosmic inflation and the nature of dark matter and dark energy. Voids, in particular, provide a unique laboratory for studying dark energy, the mysterious force driving the accelerated expansion of the universe. Because voids are underdense, they expand faster than the denser regions of the cosmic web. By studying how voids grow and change over time, astronomers can better understand the properties of dark energy and how it influences the universe's large-scale structure. Observing voids also helps refine measurements of the Hubble constant, the rate at which the universe is expanding, and can shed light on possible discrepancies between different methods of measuring this key parameter. Superclusters, on the other hand, serve as windows into the complex physics of galaxy formation and evolution. The dense environments of superclusters foster interactions between galaxies, such as mergers and close encounters, which can trigger bursts of star formation or ignite supermassive black holes at galactic centers. The hot gas in superclusters emits X-rays, providing clues about the distribution of dark matter and the gravitational forces at play. These regions also act as cosmic reservoirs, holding a large fraction of the universe's baryonic, ordinary matter, which helps scientists better understand the total matter budget of the cosmos. Despite their vast scales, voids and superclusters aren't static. Over time, gravity continues to pull material into dense regions, causing filaments to grow and voids to widen. This dynamic process means the cosmic web is still evolving, with superclusters becoming more pronounced and voids becoming emptier. By simulating this evolution with powerful supercomputers, astronomers can compare theoretical models to observed structures, testing our understanding of cosmological principles and the nature of the universe's most fundamental components. Perhaps the most profound aspect of cosmic voids and superclusters is the perspective they offer. On scales of millions or billions of light years, galaxies become dots, and entire clusters fade into the broader pattern. The cosmic web's intricate arrangement reminds us that the universe is governed by forces far larger and more enduring than any individual star or galaxy. It's a structure shaped by gravity, dark matter, and the faint echoes of the Big Bang, a pattern that stretches across the cosmos, connecting distant regions of space and time. In studying these vast voids and colossal superclusters, astronomers deepen our understanding of the universe's history, its current state, and its future trajectory. By unraveling the interplay between emptiness and abundance, between voids and clusters, we gain insight into the cosmic forces that shape everything from the smallest star to the largest galactic structure, and ultimately into the universe itself. Gravitational lenses and Einstein rings. Light doesn't always travel in a straight line. When it encounters a massive object, such as a galaxy or a cluster of galaxies, the intense gravity of that object bends the light, warping its path through space. This phenomenon, known as gravitational lensing, is not just a curious quirk of the universe. It's a powerful cosmic tool. Predicted by Einstein's general theory of relativity, gravitational lensing allows astronomers to study distant objects, map dark matter, and explore the large-scale structure of the cosmos. Gravitational lenses come in several forms. The most dramatic are strong lenses, where light from a distant source, such as a galaxy or quasar, passes near a massive foreground object. The foreground object's gravity acts like a lens, bending the light and creating multiple images of the same source. In some cases, these images form a near-perfect circle around the lens, called an Einstein ring. These rings occur when the alignment between the source, the lens, and the observer is just right. They are among the most striking visual manifestations of relativity, showing how space itself is curved by gravity. Even when the alignment isn't perfect, gravitational lensing produces fascinating patterns. Sometimes it stretches the light into arcs, while in other cases, it can produce multiple distinct images of the same background object. Each of these configurations tells a story about the mass and distribution of the lensing object. By analyzing these distorted light patterns, astronomers can infer the mass of the lensing galaxy or cluster, including the mysterious dark matter that surrounds it. Dark matter doesn't emit, absorb, or reflect light, so gravitational lensing provides one of the most direct ways to measure its presence and distribution. Gravitational lensing also reveals details about the background objects being lensed. Because the light paths are bent, we can see more of the distant source than would otherwise be possible. Lensed galaxies, for instance, appear brighter and more magnified. This allows astronomers to study galaxies that would normally be too faint or far away to observe. In a way, gravitational lensing acts as a natural telescope, giving us a closer look at the early universe and the formation of the first galaxies. One of the most exciting applications of gravitational lensing is in mapping the cosmic web, the vast network of filaments, voids, and clusters that defines a large-scale structure of the universe. By observing how light from distant quasars and galaxies is bent as it travels through the cosmic web, astronomers can reconstruct a three-dimensional map of the matter distribution in the universe. This includes not only visible matter, such as galaxies and gas, but also the elusive dark matter that makes up most of the universe's mass. Lensing also offers insights into dark energy, the mysterious force driving the accelerated expansion of the universe. By studying lensing patterns over vast distances, astronomers can measure how cosmic structures have evolved over time. These measurements help refine our understanding of how dark energy influences the growth of large-scale structures and the expansion history of the universe. Weak gravitational lensing, subtle distortions in the shapes of background galaxies, provides another powerful approach. While less visually dramatic than strong lensing, weak lensing involves analyzing tiny shifts in galaxy shapes across large areas of the sky. These shifts, averaged over many galaxies, reveal the underlying distribution of dark matter and provide clues about the nature of dark energy. Weak lensing surveys have become a key method for testing cosmological models and comparing theoretical predictions to actual observations. Some of the most famous gravitational lenses include the Einstein cross, a quasar whose light is split into 4 images by a massive foreground galaxy, and the cosmic horseshoe, a near-perfect arc formed by the lensing of a distant galaxy by a foreground cluster. These and other examples are not only visually stunning, but also scientifically rich, offering data that continues to shape our understanding of the cosmos. Looking to the future, upcoming observatories such as the James Webb Space Telescope, the Vera C. Rubin Observatory, and the Euclid mission will expand our ability to study gravitational lenses. They'll discover more lenses, measure lensing effects with greater precision, and probe deeper into the universe's history. These new observations will help answer fundamental questions about the nature of dark matter, the role of dark energy, and the origins of cosmic structures. In essence, gravitational lenses and Einstein rings serve as cosmic magnifying glasses, illuminating the universe's hidden details and uncovering the forces that shape its evolution. They remind us of the profound interconnectedness of matter, light, and gravity, and of the incredible power of Einstein's theory to describe and predict the workings of the cosmos on the largest scales. Cosmic strings and topological defects. Cosmic strings, once purely theoretical, are now among the most intriguing speculative features of our universe. These hypothetical objects are not strings in the conventional sense, but rather incredibly thin, immensely dense filaments of energy that stretch across vast expanses of space. They're considered a type of topological defect, structures that could have formed in the fabric of the universe itself during the earliest moments of cosmic history. If they exist, cosmic strings might be remnants of phase transitions that occurred as the universe cooled, much like cracks in ice form as water freezes. Unlike ordinary matter, cosmic strings are thought to be fundamentally different from anything we experience in everyday life. They would be exceedingly narrow, on the order of a proton's width, yet immensely massive, with a single kilometer of string potentially outweighing the Earth. This incredible density creates a gravitational field so intense that it could bend light and influence the movement of nearby objects, much like a black hole. However, unlike black holes, cosmic strings don't collapse into a singularity. Instead, they remain stretched and unbroken, possibly spanning thousands or even millions of light years. Cosmic strings could have profound effects on the universe's structure. Their intense gravity would cause them to leave distinctive imprints on the cosmic microwave background, CMB, the faint glow of radiation left over from the Big Bang. If strings formed shortly after the universe began, their gravitational influence would create slight temperature variations in the CMB. By searching for these subtle patterns, astronomers hope to uncover evidence of cosmic strings and gain insights into the conditions that prevailed in the universe's first moments. Beyond their potential CMB signatures, cosmic strings might also create gravitational waves, ripples in space-time that travel across the universe. As strings oscillate and move, they could emit these waves, providing a new way to detect their presence. The detection of gravitational waves by observatories like LIGO and Virgo has opened up exciting possibilities for identifying these elusive structures. If cosmic strings exist and produce gravitational waves, they would offer an entirely new window into the physics of the early universe. The concept of cosmic strings also extends into the realm of fundamental physics. They could be linked to grand, unified theories, GOTs, that attempt to unify the forces of nature, electromagnetic, weak nuclear, and strong nuclear forces, under a single framework. In such theories, cosmic strings might form as a natural consequence of the universe transitioning from a more symmetrical state to the broken symmetries we see today. In this sense, the discovery of cosmic strings would not only confirm a new type of astrophysical object, but also provide evidence for a deeper, underlying theory of everything. Some speculative ideas even suggest that cosmic strings might connect different regions of the universe or serve as conduits for exotic phenomena. For instance, two cosmic strings could intersect and form a string loop that eventually collapses, releasing energy in the form of gravitational waves. The study of these loops and their dynamics could help refine our understanding of how topological defects evolve over time. Despite their appeal, cosmic strings remain hypothetical. No direct evidence has yet been found, and their existence depends on certain conditions in the early universe that may or may not have occurred. However, as observational techniques improve, the search for cosmic strings continues. New instruments and space-based telescopes, as well as more sensitive gravitational wave detectors, may finally reveal the telltale signatures of these elusive structures. In the meantime, the idea of cosmic strings captivates both scientists and the public alike. They represent a link between the cosmos we observe today and the physics of its earliest moments, an intersection of astrophysics, cosmology, and particle physics that pushes the boundaries of our understanding. Whether or not they are eventually discovered, the concept of cosmic strings serves as a powerful reminder of how much there is still to learn about the universe's hidden dimensions and the intricate tapestry of forces that shaped its creation. Gamma ray bursts, GRBs. Gamma ray bursts, GRBs, are some of the most powerful and energetic events ever observed in the universe. In a matter of seconds, a single GRB can release more energy than our sun will emit over its entire 10 billion year lifetime. These dazzling bursts of gamma radiation, often accompanied by afterglows in X-ray, optical, and radio wavelengths, originate from some of the most extreme astrophysical processes known. Although they were discovered accidentally in the late 1960s by satellites designed to monitor nuclear tests, GRBs have since become a cornerstone of modern astrophysics, opening new windows into the violent and dynamic cosmos. GRBs come in two main flavors: long duration and short duration bursts. Long GRBs typically last from a few seconds to several minutes and are associated with the deaths of massive stars. When a star, many times the mass of the sun, reaches the end of its nuclear fuel, it collapses under its own gravity, forming a black hole or neutron star. In the process, its outer layers can be ejected at relativistic speeds, while a rapidly rotating accretion disk and intense magnetic fields launch powerful jets of particles and radiation. If one of these jets is pointed toward Earth, we see it as a GRB, a brief, incredibly bright flash of gamma rays, followed by a slowly fading afterglow. Short GRBs, on the other hand, last less than 2 seconds and are thought to arise from different mechanisms. Many are believed to result from the merger of compact objects, like neutron stars, or a neutron star with a black hole. These cataclysmic collisions generate intense gravitational waves and a burst of gamma rays, providing a unique opportunity to study both the electromagnetic and gravitational wave signals from the same event. The first confirmed association between a short GRB and a neutron star merger came in 2017, marking a major milestone in multi-messenger astronomy. The distances to GRBs are staggering. Many originate billions of light years away from some of the earliest galaxies in the universe. In fact, GRBs serve as cosmic lighthouses that can illuminate the distant universe, providing insights into the formation of stars, the evolution of galaxies, and the conditions of the early cosmos. By studying the light from a GRB's afterglow, astronomers can analyze the gas and dust in the host galaxy, gaining clues about the environment in which the burst occurred. This makes GRBs valuable probes of cosmic history. The sheer power of GRBs also makes them relevant to other areas of astrophysics. For example, their intense radiation can ionize vast regions of space, affecting the chemical composition of the surrounding interstellar medium. Some researchers have even speculated that nearby GRBs could have had an impact on Earth's biosphere, potentially causing mass extinctions or influencing the development of life. While this remains a topic of debate, it highlights the potential for GRBs to shape the environments of distant and even local cosmic regions. Recent advances in technology and observational techniques have revolutionized our understanding of GRBs. Dedicated missions like NASA's Swift Observatory and the Fermi Gamma Ray Space Telescope have dramatically increased the number of detected bursts and provided detailed, real-time observations of their afterglows. Ground-based telescopes then follow up on these detections, pinpointing the location of the burst and identifying its host galaxy. This combination of space-based and ground-based efforts has allowed astronomers to refine their models of how GRBs occur and what they can tell us about the universe. Another frontier in GRB research involves gravitational waves. When compact objects merge, they produce not only a short GRB, but also a burst of gravitational waves that can be detected by observatories like LIGO and Virgo. The simultaneous observation of gamma rays and gravitational waves from the same event provides a wealth of information, from the properties of the merging objects to the nature of the jets and the environment around them. This multi-messenger approach represents a major step forward in understanding the most energetic events in the cosmos. Looking ahead, the next generation of observatories, including more sensitive gamma-ray detectors and advanced gravitational wave facilities, promises to uncover even more about these enigmatic bursts. With each new detection, GRBs continue to surprise and challenge our understanding of the universe. They remind us that the cosmos is not a static or serene place, but a dynamic, ever-changing realm where immense energies are unleashed in spectacular ways. By studying GRBs, we not only probe the extreme physics of black holes, neutron stars, and relativistic jets, but also gain deeper insight into the universe's history, structure, and ongoing evolution. Hypervelocity stars. In the quiet darkness of interstellar space, most stars move at relatively modest speeds, tracing the gravitational contours of the Milky Way's spiral arms. But hidden among these celestial neighbors are the daredevils of the galaxy, hypervelocity stars. These are stars hurtling through the cosmos at extraordinary speeds, several hundred to thousands of kilometers per second, fast enough to escape the gravitational pull of the Milky Way entirely. Their incredible velocities make them some of the most unusual stellar objects known, raising questions about their origins and the forces that set them on their dramatic trajectories. Hypervelocity stars were first theorized in the late 1980s, but the first one was discovered in 2005. Since then, only a few dozen have been identified, making them relatively rare and highly prized by astronomers. What sets these stars apart is not just their speed, but also the story of how they achieved it. Unlike stars in normal stellar orbits, hypervelocity stars are thought to have been ejected from their original environments by powerful gravitational slingshots. One leading explanation for hypervelocity stars involves interactions with the supermassive black hole at the center of the Milky Way, known as Sagittarius A. In this scenario, a binary star system strays too close to the black hole. The intense gravitational forces tear the binary apart, capturing one star while flinging the other outward at tremendous speeds. The star that escapes becomes a hypervelocity star, racing away from the galactic center on a path that can carry it entirely out of the Milky Way. This mechanism, first proposed by astrophysicists Jack Hills and Warren Brown, is consistent with the trajectories and velocities of several observed hypervelocity stars. Other possible origins for hypervelocity stars include interactions with massive star clusters or close encounters with compact objects like neutron stars or intermediate mass black holes. Some hypervelocity stars may even come from outside the Milky Way, having been accelerated in other galaxies before crossing into our own. The diversity of potential launch mechanisms makes these stars valuable tools for studying the dynamics of the Milky Way and beyond. Hypervelocity stars are often young, hot, and massive, characteristics that make them easier to detect against the backdrop of older, cooler stars in the galactic halo. Their high speeds and unusual trajectories stand out in surveys that measure stellar velocities, helping astronomers pinpoint their locations and track their motions. Once identified, these stars provide a wealth of information about the environments they came from and the forces that shape their journeys. One of the most fascinating aspects of hypervelocity stars is the glimpse they offer into the behavior of Sagittarius A. While black holes are famously difficult to study directly, the stars they eject carry information about the conditions near these gravitational monsters. By analyzing the speeds, directions, and compositions of hypervelocity stars, astronomers can infer details about the black hole's mass, the distribution of stars and gas near the galactic center, and the strength of tidal forces in that region. These insights help build a clearer picture of the Milky Way's core and its complex gravitational dynamics. Beyond their connection to the galactic center, hypervelocity stars also serve as probes of the Milky Way's outer halo and the intergalactic medium. As they speed away from the galaxy, they traverse regions of space that are sparsely populated and difficult to study. By observing their interactions with surrounding gas and tracing their trajectories, astronomers can learn about the density, composition, and temperature of the tenuous material in these distant regions. In this way, hypervelocity stars act as natural laboratories for understanding the large-scale structure of the galaxy and its cosmic environment. Hypervelocity stars may also provide clues about the ultimate fate of the Milky Way and its interactions with nearby galaxies. Their trajectories can reveal the overall gravitational influence of the galaxy's dark matter halo, offering indirect measurements of the distribution and quantity of dark matter. By comparing the observed velocities of hypervelocity stars to theoretical models, scientists can refine their understanding of how dark matter shapes the galaxy's structure and evolution. As technology advances, the search for hypervelocity stars is expanding. Upcoming surveys with next-generation telescopes and instruments will likely uncover more of these rare objects, providing larger samples and more detailed data. This will not only enhance our understanding of their origins and characteristics, but also open new windows into the physics of extreme gravitational interactions. In essence, hypervelocity stars are not just high-speed curiosities. They are vital clues to some of the most profound mysteries in astronomy. By studying their motions, origins, and environments, we gain insights into the behavior of black holes, the dynamics of galaxies, and the nature of the dark matter that holds the cosmos together. Hypervelocity stars remind us that even in the seemingly stable expanse of space, extraordinary forces can launch stars on incredible journeys, taking them beyond the boundaries of their home galaxies and into the vast, unexplored reaches of the universe. Interstellar clouds and nebulae. Interstellar clouds and nebulae are some of the most stunning and intriguing phenomena in the cosmos. These vast regions of gas and dust exist in the space between stars, forming the raw material from which new stars and planets are born. They come in many shapes, sizes, and compositions, ranging from dark, dense molecular clouds to brightly glowing emission nebulae, each offering unique insights into the complex processes that shape galaxies and their stellar populations. One of the most familiar types of interstellar clouds is the molecular cloud, so named because the cool temperatures within these regions allow hydrogen to exist in molecular form. These clouds are the cradles of star formation. Within them, pockets of gas can collapse under gravity, heating up and igniting nuclear fusion to create new stars. The densest parts of these clouds can give rise to stellar clusters where multiple stars form in close proximity, often accompanied by nascent planetary systems. Studying these regions helps astronomers understand how stars like our Sun emerge from the interstellar medium. Molecular clouds are not homogeneous. They contain intricate structures such as filaments, cores, and voids. These structures result from a combination of processes, including turbulence, magnetic fields, and gravitational interactions. The interplay of these forces creates a dynamic environment where gas and dust flow, collide, and accumulate, setting the stage for star formation. Observations at radio and infrared wavelengths, which can penetrate the dense dust, reveal the complex networks of filaments and the compact regions where new stars are forming. By mapping these clouds, astronomers can trace the life cycle of star-forming material. In addition to molecular clouds, the universe is home to a wide variety of nebulae. Emission nebulae, such as the famous Orion Nebula, shine brightly due to the ultraviolet radiation from young, hot stars that ionize the surrounding hydrogen gas. As the electrons recombine with protons, they emit light at specific wavelengths, producing the characteristic red glow of ionized hydrogen. These nebulae are not only visually spectacular, but also key laboratories for understanding the processes of stellar birth and the feedback effects of massive stars on their environments. Reflection nebulae, by contrast, do not emit light of their own. Instead, they scatter the light of nearby stars, creating a bluish hue. This scattering occurs because interstellar dust particles are comparable in size to the wavelengths of blue light, causing shorter wavelengths to be scattered more efficiently. The study of reflection nebulae provides insights into the composition and size distribution of interstellar dust grains, as well as the properties of the stars that illuminate them. Dark nebulae are another fascinating category. These dense clouds of gas and dust are so thick that they obscure the light of background stars, appearing as dark patches against the brighter backdrop of the Milky Way. Famous examples include the Horsehead Nebula and the Coalsack Nebula. While these regions may seem inert at first glance, they often contain the seeds of future star formation. Observing dark nebulae in different wavelengths reveals hidden protostars and the initial stages of molecular cloud collapse. Nebulae also provide a window into the final stages of stellar evolution. Planetary nebulae, despite their misleading name, are the remnants of medium-sized stars that have shed their outer layers as they transition into white dwarfs. The expelled gas forms intricate, often symmetrical shapes, illuminated by the dying star's remaining heat and radiation. These beautiful structures are a fleeting phase in the life cycle of stars, offering a glimpse of our sun's distant future and the processes that enrich the interstellar medium with heavier elements. Supernova remnants represent another class of nebulae, formed when massive stars end their lives in violent explosions. The shockwaves from these events sweep up interstellar material, creating expanding shells of glowing gas. The study of supernova remnants reveals details about the composition of the star's interior, the energetics of the explosion, and the enrichment of the surrounding medium with elements heavier than iron. These remnants play a crucial role in distributing metals throughout the galaxy, seeding future generations of stars and planets with the ingredients for complex chemistry and potentially life. Interstellar clouds and nebulae are not isolated phenomena. They interact with their surroundings, responding to the gravitational pull of nearby stars and the larger structure of the galaxy. The radiation from massive stars, stellar winds, and shockwaves from supernovae all shape these clouds, triggering new waves of star formation or dispersing them into the broader interstellar medium. These interactions help drive the cyclical process of stellar birth, death, and renewal that governs the evolution of galaxies. In recent years, new observational tools have transformed our understanding of these structures. Advanced radio telescopes, space-based infrared observatories, and high-resolution imaging instruments have unveiled the complex interplay of physics and chemistry within interstellar clouds. Scientists are now able to map the distribution of various molecules, measure magnetic fields, and observe the earliest stages of star formation. This growing body of data not only enhances our understanding of how stars and planets form, but also helps refine models of galaxy evolution and the cosmic origins of elements. Interstellar clouds and nebulae are more than just beautiful cosmic vistas. They are fundamental to the story of how galaxies grow and change over time. They connect the life cycles of stars to the larger scale dynamics of the universe, serving as both the starting point for new stellar generations and the repositories of the building blocks of life. As we continue to study these awe-inspiring regions, we gain a deeper appreciation for the interconnected processes that shape our cosmic environment and our place within it. Supernova remnants. When a massive star exhausts its nuclear fuel, it ends its life in a spectacular cataclysm known as a supernova. The outer layers of the star are blasted into space, creating an expanding shell of gas and dust, a supernova remnant. These remnants, glowing with the energy of the initial explosion and the radiation from shock-heated material, are among the most beautiful and scientifically valuable objects in the universe. They provide a glimpse into the violent processes that forge heavy elements, recycle material into the interstellar medium, and help shape the evolution of galaxies. One of the defining features of a supernova remnant is its intricate, often filamentary structure. In the aftermath of the explosion, shock waves plow through the surrounding gas and dust, compressing and heating the material to millions of degrees. This heating causes the remnant to emit light across a wide range of wavelengths from X-rays and ultraviolet to visible and radio waves. Each of these wavelengths reveals different aspects of the remnant's composition and physical state. X-rays, for example, highlight the hottest regions and trace the shock fronts, while optical and infrared observations can reveal cooler, denser clumps of material and the distribution of heavy elements. One of the most famous supernova remnants is the Crab Nebula, the result of a supernova explosion recorded by Chinese astronomers in 1054 CE. Today, the Crab Nebula is a bright, complex structure that continues to expand at more than 1,000 kilometers per second. At its core lies a pulsar, a rapidly spinning neutron star that emits beams of radiation and powers the nebula's brilliance. The Crab Nebula and its pulsar have provided invaluable insights into the physics of supernovae, the behavior of neutron stars, and the mechanisms that produce high-energy particles and radiation in these extreme environments. Supernova remnants also serve as laboratories for studying the production of elements. During the explosion, the star's core undergoes rapid nuclear reactions, creating heavy elements such as iron, nickel, and calcium. These newly forged elements are then ejected into space, mixing with the surrounding interstellar medium. By analyzing the spectra of supernova remnants, astronomers can measure the abundances of these elements and trace how they contribute to the chemical enrichment of the galaxy. In this way, supernova remnants reveal the origins of many of the elements essential for life, including oxygen, carbon, and nitrogen. Another key feature of supernova remnants is their interaction with the surrounding environment. As the shock waves expand, they can trigger new waves of star formation by compressing nearby molecular clouds. This process, known as triggered star formation, links the death of one star to the birth of others, demonstrating the cyclical nature of the universe. In other cases, the shock waves can heat and ionize interstellar gas, creating regions of glowing plasma that illuminate the structure of the galaxy. The impact of a supernova remnant on its surroundings can extend for tens or hundreds of light years, shaping the dynamics and appearance of the local interstellar medium. Supernova remnants also produce cosmic rays, high-energy particles that travel through the galaxy at nearly the speed of light. The shock waves of a supernova remnant accelerate these particles, giving them their incredible energy. Cosmic rays play a significant role in the interstellar medium, influencing magnetic fields, contributing to the ionization of gas, and affecting the formation of molecular clouds. By studying supernova remnants, scientists gain insights into how cosmic rays are produced and how they interact with the galaxy on large scales. Recent advances in telescopes and observatories have brought supernova remnants into sharper focus than ever before. Instruments like NASA's Chandra X-ray Observatory and ESA's XMM Newton have provided detailed X-ray images of remnants, revealing intricate shock structures and hot, glowing gas. Radio telescopes have traced the magnetic fields within remnants, showing how these fields shape the expansion and evolution of the debris. Optical and infrared telescopes have captured the stunning, colorful filaments of gas and dust, helping astronomers map the distribution of elements and understand the remnants' overall geometry. Some remnants, such as the Veil Nebula, are so large and luminous that they can be seen with small telescopes or even binoculars, making them popular targets for amateur astronomers. But even these visually impressive objects are just a fraction of the remnants scattered throughout our galaxy. Many more are hidden behind thick clouds of dust or lie in regions of the sky that are difficult to observe. As new instruments come online and survey techniques improve, astronomers expect to find and study many more supernova remnants, expanding our knowledge of these cosmic phenomena. Supernova remnants are more than just the ashes of dead stars. They are dynamic, evolving structures that link the life cycles of stars to the larger processes of galactic evolution. By studying them, astronomers not only uncover the details of stellar explosions, but also gain insights into the origins of elements, the behavior of extreme environments, and the interconnected nature of the universe. Through their complex, luminous patterns, supernova remnants offer a vivid reminder of the powerful forces at work in the cosmos and their role in shaping the galaxies we see today. Tidal disruption events. Tidal disruption events, or TDEs, occur when a star ventures too close to a supermassive black hole and is torn apart by its immense gravitational forces. In such encounters, the black hole's tidal forces, differences in gravitational pull across the star's body, stretch and compress the star, shredding it into streams of gas. This material doesn't simply vanish. Instead, part of it spirals into the black hole, forming a temporary accretion disk that emits enormous amounts of light and energy. The result is a dramatic flare, often observed in X-rays, ultraviolet, and visible light, which can outshine the combined light of all the stars in the host galaxy for months or even years. TDEs offer astronomers a rare opportunity to witness the feeding habits of supermassive black holes. Normally, black holes in most galaxies are relatively quiescent, without significant amounts of material falling into them. But during a TDE, the sudden influx of stellar debris provides a momentary burst of activity, revealing clues about the black hole's properties and the conditions near its event horizon. These events also shed light on the dynamics of stars in the crowded regions around black holes, showing how close encounters can lead to such spectacular displays. The physics of a TDE is both violent and intricate. When a star approaches a black hole, the side closer to the black hole feels a much stronger gravitational pull than the side farther away. This tidal stretching becomes so extreme that it rips the star into a long stream of gas. The innermost parts of this stream spiral toward the black hole, while the outer parts escape into space. The material that falls inward forms a temporary, highly luminous accretion disk, heating to millions of degrees and radiating intense energy. The radiation can be detected by telescopes across a range of wavelengths, providing a direct signature of the event. TDEs are not just spectacular light shows. They also serve as natural laboratories for studying extreme physics. The intense gravitational forces involved push the limits of our understanding of general relativity, and the rapidly changing conditions near the black hole offer insights into the processes of accretion, jet formation, and the production of high-energy particles. By examining the light curves, spectra, and polarization of TDE flares, astronomers can probe the properties of the black hole itself, including its mass, spin, and the structure of the surrounding spacetime. Recent advances in observational technology have made TDEs a hot topic in astrophysics. Surveys using wide-field optical telescopes, such as the Zwicky Transient Facility and the All-Sky Automated Survey for Supernovae, have increased the number of known TDEs by scanning large areas of the sky for transient events. Meanwhile, X-ray and ultraviolet observatories provide detailed follow-up observations, revealing the high-energy emission from the accretion disk. These multi-wavelength studies allow scientists to piece together a comprehensive picture of the tidal disruption process and its aftermath. TDEs also have implications for understanding the environments around supermassive black holes. By measuring how often these events occur, astronomers can infer the number of stars near the black hole and the distribution of their orbits. This information helps refine models of galactic nuclei and sheds light on the complex interactions that shape the central regions of galaxies. In some cases, TDEs may even help explain why certain black holes remain active long after their galaxies have stopped forming new stars, as occasional stellar disruptions supply fresh material to fuel accretion. Beyond their astrophysical importance, TDEs also serve as cosmic markers for identifying dormant or hidden black holes. Many galaxies host supermassive black holes that are difficult to detect when not actively accreting material. A tidal disruption event can suddenly reveal the presence of an otherwise quiet black hole, providing a rare glimpse into the demographics of black holes in the universe. This helps astronomers understand how black holes grow and evolve over cosmic time. Despite their rarity, tidal disruption events have a profound impact on the regions in which they occur. The burst of energy can ionize surrounding gas, affect the dynamics of nearby stars, and alter the conditions of the galaxy's central environment. In some cases, the interaction of the stellar debris with pre-existing material can generate powerful outflows or even relativistic jets, further influencing the galaxy's structure and evolution. The bullet cluster. In the vast expanse of the universe, galaxy clusters collide on cosmic timescales, creating dramatic and revealing events. One such collision, known as the bullet cluster, 1E-657-558, has become a critical case study for understanding dark matter, the invisible substance that makes up most of the matter in the universe. This cluster, located about 3.7 billion light-years away, is actually the aftermath of two galaxy clusters smashing into each other at extraordinary speeds. The resulting collision produced a fascinating split between visible matter and dark matter, offering astronomers some of the most compelling direct evidence of dark matter's existence. The bullet cluster gets its name from the appearance of a smaller, bullet-shaped subcluster that has passed through a larger cluster. In this cosmic collision, the galaxies themselves largely pass by one another, much like a handful of sand thrown through another handful of sand. Most of the grains simply miss each other. However, the hot X-ray emitting gas that makes up most of the visible mass of the clusters behaved very differently. As the two clusters collided, the gas from each cluster slammed into the other, heating up to tens of millions of degrees and creating shock waves. This is the source of the bullet shape seen in X-ray observations. What makes the bullet cluster so extraordinary, though, is what happened to the dark matter. Unlike the hot gas, dark matter doesn't interact with itself or with normal matter through electromagnetic forces. It only interacts via gravity. As the two clusters collided, their dark matter components passed straight through each other, unaffected by the friction that slowed down the hot gas. This separation between the dark matter and the hot gas created a unique observational signature. The galaxies, tracing the dark matter's gravitational influence, are displaced from the dense X-ray gas. This phenomenon was captured using a combination of optical and X-ray observations. The Chandra X-ray Observatory revealed the glowing hot gas, while optical telescopes mapped the positions of the galaxies. The most revealing data, however, came from gravitational lensing studies. The bullet cluster's massive gravitational field distorts the light from background galaxies, a phenomenon predicted by Einstein's general relativity. By analyzing these distortions, astronomers created detailed maps of the cluster's total mass distribution. These maps showed that most of the mass is not in the hot gas, where most of the normal, visible matter resides, but instead in regions dominated by dark matter. This separation is what makes the bullet cluster such a powerful piece of evidence for dark matter. In alternative theories, such as modified Newtonian dynamics, MOND, the effects attributed to dark matter might arise from a different behavior of gravity at large scales. However, the bullet cluster's collision is hard to explain without invoking some form of invisible mass. The dark matter clearly acts like a gravitational scaffold, shaping the motions of galaxies and the bending of light, while the hot gas lags behind. This offset demonstrates that dark matter and normal matter can be physically separated in a way that aligns with our standard cosmological models. Beyond its implications for dark matter, the bullet cluster also provides insights into galaxy cluster dynamics and the growth of large-scale cosmic structures. Galaxy clusters are among the most massive bound structures in the universe, and their collisions are relatively rare and violent events. Studying these interactions helps astronomers understand how clusters form, evolve, and merge over billions of years. It also sheds light on the behavior of hot intracluster gas, the role of shock waves, and the overall distribution of matter in the universe. The bullet cluster's uniqueness has made it a cornerstone in the study of dark matter and cosmic structure, but it's not the only cluster providing such clues. Other cluster collisions, like the musket ball cluster and the Pandora cluster, Abel 2744, show similar separations between visible and dark matter components, reinforcing the case for dark matter's existence and the current cosmological paradigm. Each new observation adds to a growing body of evidence that dark matter is a real and essential ingredient of the universe. Future studies with more advanced instruments, such as next-generation X-ray observatories, deeper gravitational lensing surveys, and improved cosmological simulations, will continue to refine our understanding of the bullet cluster and other similar systems. These efforts will help answer fundamental questions about dark matter's nature. Is it made of weakly interacting particles, or something even more exotic? How does it behave on the smallest scales, and how does it fit into the overall structure of the universe? In the meantime, the Bullet Cluster stands as a cosmic monument to the unseen forces that shape the universe. By examining the aftermath of this colossal collision, astronomers have gained some of the clearest evidence yet of dark matter's reality and its profound influence on cosmic evolution. This cluster not only provides a snapshot of a dramatic moment in the universe's history, but also points the way forward in the quest to understand the universe's most mysterious substance. Fast radio bursts, FRBs. Fast radio bursts, or FRBs, are among the most enigmatic phenomena in modern astrophysics. These intense, millisecond-long pulses of radio waves originate from sources far beyond our galaxy, yet their exact nature remains a tantalizing mystery. First discovered in 2007, FRBs have captured the attention of astronomers worldwide because of their unpredictable nature, extreme energy outputs, and potential to unlock new insights into the universe's hidden structures. What makes FRBs so remarkable is their immense power. In just a few milliseconds, an FRB can release as much energy as the sun does in an entire day. These bursts are detected across the entire radio spectrum, often appearing as sudden, bright flashes that disappear almost as quickly as they arrive. Unlike pulsars, which emit regular, repeating signals, most FRBs appear to occur only once at a particular location, making them incredibly challenging to study. However, in recent years, a handful of FRBs have been found to repeat. The discovery of repeating FRBs opened a new chapter in the study of these mysterious signals. By observing repeated bursts from the same source, astronomers have been able to pinpoint their origins with greater precision and study the environments from which they emerge. One well-known repeater, FRB 121102, was traced to a small dwarf galaxy nearly 3 billion light-years away. The region surrounding it is rich in magnetic fields and ionized gas, suggesting that these conditions may play a role in generating the bursts. Despite the growing number of detected FRBs, their exact cause remains uncertain. Several theories have been proposed, ranging from natural astrophysical processes to more exotic possibilities. Some researchers suggest that FRBs originate from magnetars, highly magnetized neutron stars, undergoing sudden magnetic reconnection events or powerful starquakes. Others point to the collision of compact objects, such as neutron stars or black holes, as potential sources. Even more speculative ideas include interactions with cosmic strings or signals from advanced alien civilizations, although no evidence supports the latter. One of the key challenges in studying FRBs is their randomness. Unlike pulsars or supernovae, which have well understood origins and predictable behaviors, FRBs appear unexpectedly and disappear just as quickly. This unpredictability requires dedicated surveys and specialized radio telescopes that can scan large portions of the sky continuously. Instruments like the Canadian Hydrogen Intensity Mapping Experiment, CHIME, and Australia's ASCAP telescope have been particularly successful in identifying new FRBs and building a catalogue of events. With each new detection, astronomers refine their understanding of the conditions necessary to produce these bursts and narrow down the list of possible explanations. In addition to their mysterious origins, FRBs have proven to be powerful tools for probing the intergalactic medium. As radio waves travel from their distant sources to Earth, they pass through clouds of gas and plasma, which leave a distinctive signature on the signal. By analyzing these signatures, astronomers can measure the density and distribution of matter between galaxies, providing crucial information about the structure of the cosmic web. FRBs effectively turn the universe into a giant laboratory, allowing scientists to study the invisible components of the cosmos and map the otherwise unseen matter that binds galaxies together. FRBs also hold the potential to answer long-standing questions about the universe's fundamental properties. For example, by measuring how the polarization of radio waves from FRBs changes as they travel through different environments, astronomers can study magnetic fields on cosmic scales. These magnetic fields play a vital role in shaping galaxy evolution, influencing star formation, and driving large-scale cosmic flows. Understanding them helps piece together a more complete picture of how the universe has evolved over billions of years. As technology advances, the pace of FRB discovery is accelerating. Upcoming radio observatories and next-generation telescopes promise to detect thousands of new FRBs, expanding the known sample and increasing the odds of identifying their sources. With larger data sets, astronomers hope to determine whether all FRBs have the same origin or if multiple phenomena can produce similar signals. They also aim to find patterns that could link FRBs to specific astrophysical processes, such as supernova remnants, active galactic nuclei, or dense, star-forming regions. While the exact nature of FRBs remains one of the greatest cosmic puzzles, their study is yielding insights that go far beyond understanding these bursts alone. FRBs are revealing new details about the universe's hidden structures, the behavior of matter and magnetic fields on the largest scales, and the processes that drive the most extreme astrophysical phenomena. They remind us that the universe is still full of surprises, signals from billions of light years away that challenge our knowledge and invite us to keep exploring. As researchers continue to hunt for answers, FRBs hold the promise of transforming our understanding of the cosmos, 1 millisecond burst at a time. Unusual binary and multi-star systems. When we look at the night sky, we often think of stars as solitary objects like our sun. However, many stars are not alone. In fact, binary and multi-star systems are common throughout the galaxy, comprising pairs or even groups of stars that orbit each other due to their mutual gravitational attraction. While some of these systems are fairly straightforward, a pair of stars revolving around a common center of mass, others are far more complex and peculiar, with unusual dynamics that challenge our understanding of stellar behavior and evolution. One of the most fascinating types of binary systems is the eclipsing binary. In these systems, the orbit of the stars aligns in such a way that, from our vantage point, one star periodically passes in front of the other, causing the system's brightness to dip. These eclipses provide astronomers with a wealth of information, allowing precise measurements of the star's masses, sizes, and orbital parameters. Some eclipsing binaries even exhibit periodic changes in the timing of their eclipses, suggesting the presence of additional unseen companions, either other stars or large planets, making them an excellent laboratory for studying the formation and evolution of multiple star systems. Another intriguing type of binary system involves white dwarfs, neutron stars, or black holes paired with a companion star. In these systems, material from the companion star can flow onto the compact object, forming an accretion disk that emits X-rays or other high-energy radiation. This process can lead to remarkable phenomena, such as X-ray binaries or cataclysmic variables, where the interplay between the two stars produces outbursts, intense magnetic fields, and relativistic jets. Such systems provide critical insights into the end stages of stellar evolution and the behavior of matter in extreme gravitational and magnetic environments. Some binary systems are so close that their stars physically touch or share a common envelope of gas. These so-called contact binaries often evolve dramatically over time. In some cases, the interaction can lead to stellar mergers, producing a single, more massive star. In others, the shared envelope can be ejected entirely, revealing a tight binary of compact objects that may eventually coalesce into a single black hole or neutron star. These systems are not only interesting from an astrophysical perspective, but also serve as potential progenitors for some of the most energetic events in the universe, including supernovae and gravitational wave sources. Multi-star systems, where three or more stars orbit each other, add another layer of complexity. These configurations often have hierarchical arrangements, with two stars forming a tight binary and a third star orbiting at a greater distance. Such systems can remain stable for long periods, but their intricate gravitational interactions can cause unpredictable changes in their orbits over time. In some cases, the presence of a distant companion can induce perturbations that lead to the stars spiraling together or ejecting one member from the system altogether. These dynamics provide valuable test cases for gravitational theories and help refine our models of star cluster evolution. Beyond their intrinsic fascination, unusual binary and multi-star systems have important implications for our understanding of the cosmos. They play a key role in the chemical enrichment of galaxies, as interactions between stars in these systems can lead to phenomena such as supernova explosions that spread heavy elements into the interstellar medium. They also serve as critical benchmarks for testing theoretical models of stellar structure, nuclear fusion processes, and the interplay of gravity and radiation. As observational techniques improve, astronomers continue to discover new and increasingly exotic binary and multi-star systems. High-resolution imaging, long-term monitoring, and advanced simulations have revealed systems with highly elliptical orbits, stars that exchange mass in unexpected ways, and systems that defy easy classification. Each new discovery adds to the growing picture of how stars live and die, how they interact with their neighbors, and how their combined effects shape the evolution of galaxies over billions of years. In many ways, these unusual stellar systems are like cosmic laboratories, allowing us to study processes that cannot be replicated on Earth. By understanding their peculiarities, we not only learn more about stars themselves, but also gain insights into the broader workings of the universe. These dynamic, complex relationships remind us that even in the vastness of space, stars are not solitary. They often dance with partners or gather in small, gravitationally bound communities, creating patterns of motion and energy that illuminate the fundamental forces shaping the cosmos. The Diamond Planet, 55, Cancri. Imagine a planet so exotic that it challenges the way we think about worlds beyond our solar system. 55. Cancri, a so-called super-Earth, located 40 light-years away in the constellation Cancer, is one of the most intriguing exoplanets ever discovered. It's often nicknamed the Diamond Planet because some researchers believe its composition may include a significant amount of carbon, potentially in the form of diamond. Although later studies have cast doubt on this specific claim, the notion of a carbon-rich planet has captured the imagination of scientists and the public alike, making 55 Cancri a fascinating case study in the diversity of alien worlds. 5 Cancri was discovered in 2004 as part of a multi-planet system orbiting the star 55 Cancri a sun-like star with at least 5 known planets. What sets 55 Cancri apart is its extreme proximity to its host star. The planet completes a full orbit in just 18 hours, placing it so close that its surface temperatures soar to over 2,000 degrees Fahrenheit, about 1,100 degrees Celsius. This intense heat makes the planet an unlikely candidate for habitability, but it also makes it a unique natural laboratory for studying planetary formation and the chemistry of rocky worlds in extreme environments. One of the initial theories about 55 Cancri A was that it might be composed primarily of carbon-based materials, such as graphite and diamond. This hypothesis emerged from the star's unusually high carbon-to-oxygen ratio, which suggested that the protoplanetary disk from which 55 Cancri E formed might have been rich in carbon. If true, the planet could have a crystalline structure unlike anything in our solar system, with a mantle potentially dominated by diamond rather than silicate rocks. However, subsequent observations and modeling have challenged this idea. Studies using the Spitzer Space Telescope and other instruments have provided conflicting data about the planet's atmosphere, composition, and even its density. Some findings suggest that 55 Cancri E is more similar to a silicate-based super-Earth with a high-pressure water or volatile-rich atmosphere. In this view, rather than being a diamond-studded world, it might have a rocky core surrounded by a thick atmosphere of carbon dioxide or other greenhouse gases, contributing to its extreme temperatures. One of the most puzzling aspects of 55 Cancri E is its apparent variability. Observations show that the planet's temperature seems to fluctuate over time, with one hemisphere often appearing much hotter than the other. This could indicate a dynamic atmosphere, volcanic activity, or the presence of molten lava or oceans on one side of the planet. Alternatively, it might suggest that the planet is tidally locked, with one side perpetually facing its star and the other in permanent darkness. In either case, these temperature shifts hint at a complex, changing environment that defies easy explanation. 55. Cancri E also challenges our understanding of how planets form and evolve. If the initial diamond planet hypothesis is even partially correct, it would imply that planets can emerge from protoplanetary disks with very different chemical compositions than those in our solar system. It would also suggest that carbon-rich planets might be common around certain types of stars, opening up new possibilities for planetary diversity and the chemistry of exotic worlds. Even if the diamond planet idea ultimately proves incorrect, 55 Cancri A remains a valuable subject of study. Its extreme heat, short orbital period, and potential atmospheric variability make it a unique example of a super-Earth on the edge of our current models. By studying it in detail, scientists can refine their theories about how planets interact with their stars, how atmospheres behave under intense radiation, and what types of conditions lead to the formation of planets that are so radically different from those in our solar system. Future missions, including next-generation space telescopes and improved ground-based instruments, may help resolve the mysteries surrounding 55 Cancri E. These observations could provide more precise measurements of its atmosphere, surface composition, and thermal properties. If we can uncover the true nature of this planet, whether it's a diamond-rich world, a lava-covered super-Earth, or something entirely unexpected, it will deepen our understanding of the variety and complexity of exoplanets in the galaxy. In the end, 55 Cancri E serves as a reminder that the universe is full of surprises. Each discovery pushes the boundaries of what we think is possible, revealing a cosmos more diverse and wondrous than we ever imagined. Whether it glitters with diamond crusts or seethes with molten lava, 55 Cancri E challenges our perceptions and inspires new questions about the myriad ways planets can form, evolve, and exist in the vastness of space. The enigmatic Planet 9. For decades, astronomers have debated whether our solar system harbors a large, hidden planet far beyond the orbit of Neptune. This hypothetical world, often referred to as Planet 9, has captured the imagination of both scientists and the public. Unlike Pluto, which resides in the icy Kuiper belt and was demoted to dwarf planet status, Planet 9 is thought to be a much larger body, perhaps 4 to 10 times the mass of Earth. Its existence remains unconfirmed, but intriguing clues suggest that something massive might be lurking in the distant reaches of the solar system. The search for Planet 9 began in earnest in 2016 when researchers Konstantin Batygin and Mike Brown of Caltech published a study proposing its existence. They were motivated by a curious pattern among certain trans-Neptunian objects, TNOs, which are small, icy bodies located beyond Neptune. These objects had orbits that seemed to be clustered together, a configuration that couldn't easily be explained by the known planets alone. Batygin and Brown hypothesized that a distant, undiscovered planet was gravitationally shepherding these TNOs into their unusual orbital alignments. If Planet 9 exists, it would reside far from the Sun, with an orbit hundreds of times farther out than Earth's. Estimates suggest it could take thousands of years to complete a single circuit around the Sun. Such a distant orbit would make the planet incredibly faint and difficult to detect with current telescopes. Moreover, its position in the sky remains uncertain, adding to the challenge of pinpointing its location. These factors help explain why this potential planet has remained hidden for so long. While the clustering of TNO orbits is the strongest indirect evidence for Planet 9, other hints have emerged. For example, some researchers have suggested that the observed tilts of certain distant objects' orbits could also be influenced by the gravitational pull of a massive, unseen planet. Additionally, simulations of the early solar system indicate that a planet of this size could have been ejected into a distant orbit as the giant planets Jupiter, Saturn, Uranus, and Neptune migrated to their current positions. If Planet 9 was indeed pushed outward, it might now lie in the cold, dark outskirts of the solar system, far beyond the Kuiper belt. Despite these tantalizing hints, not everyone is convinced that Planet 9 exists. Some astronomers argue that the clustering of TNO orbits could be a statistical fluke, or that the observations may be biased due to the limitations of current surveys. Others have proposed alternative explanations, such as a disk of small, icy objects exerting a collective gravitational influence rather than a single massive planet. As a result, the debate over Planet 9 continues, and the astronomical community remains divided on whether this elusive world is real or merely a mathematical curiosity. If Planet 9 does exist, finding it would have profound implications for our understanding of the solar system. Its discovery would challenge current models of planetary formation, as it would indicate that a massive planet could form far from the Sun or migrate to such a distant orbit under the right conditions. It would also reshape our view of the solar system's outer regions, revealing that the Sun's gravitational influence extends much farther than previously thought. In the years since Batygin and Brown's initial proposal, the hunt for Planet 9 has intensified. Astronomers are conducting dedicated surveys with powerful telescopes, scanning vast areas of the sky in search of a faint, slow-moving object. Advances in data analysis techniques, coupled with upcoming observatories like the Vera C. Rubin Observatory, are expected to improve the chances of detecting this mysterious planet. If and when it is found, it would be a discovery on par with the first detections of Uranus and Neptune, expanding our solar system's boundaries and revealing a new world waiting to be explored. Even if Planet 9 remains elusive, the search itself has yielded valuable scientific insights. The detailed study of TNOs and their orbits has deepened our understanding of the outer solar system, the Kuiper belt, and the dynamics of distant icy bodies. It has also sparked new theoretical work on planetary migration, orbital resonance, and the formation of small, icy worlds. In this sense, the quest for Planet 9 is about more than just finding another planet. It's about uncovering the hidden architecture of our solar system and piecing together the story of its formation and evolution. White hole theories. In the strange and speculative landscape of theoretical physics, white holes stand out as some of the most intriguing and puzzling objects ever proposed. While black holes are well known as regions of space-time where gravity is so intense that nothing, not even light, can escape, white holes represent the theoretical opposite, objects that cannot be entered from the outside and instead emit matter and energy, effectively pushing everything away. Though no observational evidence for white holes exists, the concept continues to intrigue physicists, offering a fascinating thought experiment about the nature of space-time, singularities, and the flow of time itself. The idea of white holes arises naturally from Einstein's equations of general relativity. Mathematically, the same solutions that describe black holes can also describe white holes. But the key difference lies in the direction of time. In a black hole, matter and energy fall inward and are seemingly lost to the outside universe. In a white hole, this process is reversed. Matter and energy flow outward, and nothing can cross the event horizon from the outside in. In essence, a white hole would appear as a burst of material and radiation pouring into the universe, an event that would seem extraordinarily bright and chaotic if it were ever observed. Some theories suggest that white holes could be connected to black holes through a wormhole or a bridge-like structure in space-time. This idea, often referred to as the Einstein-Rosen bridge, imagines that a black hole in one part of the universe might be linked to a white hole elsewhere, allowing matter to pass through the black hole's event horizon and emerge from the white hole's horizon. In such a scenario, what falls into the black hole would not be lost forever, but would reappear in a different region of space-time, possibly even in another universe. This concept, while speculative, has led to intriguing discussions about the fundamental structure of space-time and the possibility of shortcuts through the cosmos. Another area of interest involves the potential role of white holes in explaining certain cosmological phenomena. Some researchers have speculated that white holes might be responsible for gamma-ray bursts, the most energetic explosions observed in the universe. While no direct evidence links white holes to these events, the idea that a previously unknown type of astrophysical object could produce such extraordinary energy is an enticing possibility. Additionally, white holes have been considered as a potential explanation for certain anomalies in high-energy astrophysics, though these ideas remain highly theoretical and are not widely accepted. White holes also raise profound questions about the nature of time and causality. If white holes exist, they would represent regions of space-time where the normal rules of cause and effect might break down. Since nothing can enter a white hole, it effectively seals off a portion of space-time from external influences. This leads to challenging questions about what triggers the formation of a white hole, how long it might exist, and what conditions would cause it to decay or transform into another state. Such questions push the boundaries of our understanding of physics and test the limits of Einstein's theory of general relativity. In quantum gravity and certain speculative theories, white holes could have connections to the early universe. Some cosmologists have suggested that the Big Bang itself might have been a white hole-like event, a one-time outpouring of matter and energy into our universe. While this idea remains far from mainstream, it highlights the potential importance of white holes in exploring the origins of the cosmos. If white holes were more than just mathematical solutions, if they had some physical reality, they might provide insights into how the universe began and how space-time behaves under extreme conditions. Despite their appeal as a theoretical construct, white holes remain entirely hypothetical. No telescope, particle detector, or observational survey has found evidence of a white hole, and many physicists believe they may not exist in our universe at all. Nonetheless, their mathematical consistency within general relativity keeps them on the radar of theoretical physicists, and ongoing research into quantum gravity, black hole thermodynamics, and the nature of space-time might one day offer more clarity on whether white holes could exist and what their role in the universe might be. Dyson spheres and megastructures. Imagine an alien civilization so advanced that it decides to build a structure that encases its star. This vast construct, often called a Dyson sphere, would harvest the star's energy on an unimaginable scale, potentially providing power for countless technological marvels, interstellar travel, and the sustenance of an entire planetary system. While this might sound like science fiction, the concept has long been a serious subject of study among astrophysicists, futurists, and those pondering the possibilities of advanced civilizations in the universe. The original idea was proposed by the physicist and mathematician Freeman Dyson in a 1960 paper. He suggested that as a civilization grows, its energy needs will increase far beyond what can be supplied by planetary resources. To keep progressing, such a society might construct an enormous structure around its star to capture a large percentage of its output. The harvested energy would then be used to power everything from massive computing systems to planetary-scale environmental control, effectively turning the star into a vast power plant. A true Dyson sphere, one that completely surrounds a star, would be an engineering project of unfathomable proportions. The challenges are not just technical, but also material. The sheer amount of matter needed to construct a solid shell around a star would dwarf anything we can currently imagine. This is why most practical discussions about Dyson spheres focus on the idea of a Dyson swarm rather than a rigid sphere. A Dyson swarm would consist of a vast number of satellites or habitats, each orbiting the star at a safe distance. These individual units would collectively capture energy, providing the same benefits as a solid sphere while being far more feasible. If an advanced civilization managed to build such a structure, it would be visible to us, at least indirectly. A Dyson sphere or swarm would block a significant portion of the star's light. From Earth, we might see the star's brightness dimmed or observe an unusual spectrum of light. For instance, the captured energy would likely be re-radiated as heat, resulting in a distinctive infrared signature. This has led astronomers to search for candidate stars, whose infrared emissions suggest they might be surrounded by artificial structures. While no definitive evidence of Dyson spheres has been found, the ongoing search continues to intrigue scientists. Dyson spheres are not the only type of megastructure hypothesized by futurists and physicists. Other ideas include ring worlds, vast bands encircling a star at the same orbital distance as a planet, or even the entire star-encircling habitat proposed in Larry Niven's science fiction. There are also concepts of stellar engines, which involve massive constructs that capture a star's energy to propel it and its planets through space. These ideas, while speculative, are grounded in the basic principle that advanced civilizations might seek to harness energy and resources on a stellar scale. Beyond their technological allure, Dyson spheres and similar megastructures have profound implications for our understanding of the cosmos. If we ever detect such a construct, it would confirm the existence of extraterrestrial intelligence and suggest that the development of technology can continue far beyond our current stage. It would also raise questions about the ethics, motivations, and long-term goals of a civilization that undertakes such a monumental project. In the search for alien megastructures, astronomers have examined a range of data from telescopes and space missions. Some have even speculated that unexplained dimming events in certain stars, like those observed in Tabby's star, might be consistent with the presence of a large-scale construct. While natural explanations remain the most likely, these observations inspire creative thinking and encourage researchers to consider scenarios that push the boundaries of our imagination. In addition to their potential detectability, Dyson spheres offer a unique perspective on energy use and sustainability. If humanity were to one day aspire to build a Dyson swarm or similar construct, it would signal a profound shift in how we think about energy production, resource utilization, and the future of our species. The concept encourages long-term thinking and reminds us that our sun's energy is not only vast, but also one of the most consistent and reliable power sources available. Whether or not Dyson spheres ever become a reality, the idea serves as a powerful symbol of technological ambition and the boundless potential of advanced civilizations. It challenges us to think beyond planetary scales, to consider the full resources of a star, and to imagine a future where humanity, or another intelligent species, taps into the full power of the cosmos. The strange behavior of pulsar planets. Pulsars are some of the most extraordinary objects in the universe, rapidly spinning neutron stars that emit powerful beams of electromagnetic radiation. As they rotate, these beams sweep across the sky, creating a regular pulse of light that can be detected by radio telescopes on Earth. Pulsars themselves are incredible astrophysical laboratories, but what makes them even more fascinating is that a handful of them have been found to host planets, bizarre, exotic worlds in environments that defy conventional ideas about planetary formation and survival. The first confirmed exoplanets ever discovered, in fact, were not orbiting a sun-like star, but a pulsar. In 1992, astronomers Alexander Wolszczan and Dale Frail identified two planets orbiting the pulsar PSR B257+12. These so-called pulsar planets were an unexpected discovery, as the conditions around pulsars seemed far too hostile for planets to exist. Pulsars are formed in the aftermath of a supernova explosion, a cataclysmic event that obliterates the star's outer layers and leaves behind a dense core. The violent birth of a pulsar, along with the intense radiation it emits, was thought to make it highly unlikely for planets to form or survive. Yet pulsar planets do exist. The ones around PSR B1257+12 are similar in mass to Earth, but they orbit extremely close to their host, subjected to relentless radiation and powerful magnetic fields. Their presence raises compelling questions about how they came to be. One possibility is that these planets formed after the supernova, from a disk of material that settled around the pulsar. Another scenario suggests that they could be the remnants of a destroyed star or a disrupted companion, perhaps a white dwarf or a massive planet, that was torn apart by the pulsar's gravity and then reassembled into new planetary bodies. Regardless of their origin, the fact that planets can exist in such extreme conditions demonstrates the resilience and diversity of planetary systems. The conditions on pulsar planets are almost unimaginable. Bathed in a continuous barrage of high-energy radiation, these planets would have no protective atmosphere as we understand it. Their surfaces might be stripped bare, bombarded by charged particles from the pulsar's magnetosphere. Any water or volatile compounds would likely have been long since evaporated or destroyed. The relentless radiation would also prevent the formation of complex molecules or organic life as we know it. In many ways, pulsar planets represent the opposite of the idyllic, habitable worlds that astronomers often hope to find. Despite their inhospitable environments, pulsar planets offer unique opportunities for scientific research. Because pulsars emit incredibly regular pulses of light, even tiny gravitational influences, such as those from orbiting planets, can be detected with remarkable precision. This means that pulsar planets can be identified and studied in ways that would be difficult or impossible for planets around normal stars. In some cases, the timing variations in a pulsar signal are so sensitive that they can reveal the mass, orbit, and even the composition of these planets. Pulsar planets thus serve as powerful tools for testing theories of planetary dynamics and probing the properties of neutron stars. Another intriguing possibility is that pulsar planets could help us understand the late stages of stellar evolution. Their presence indicates that planetary systems might not always be destroyed when their host star dies. Instead, some planets, or the building blocks of planets, might survive the most extreme conditions and reform around the remnant. This raises questions about the ultimate fate of our own solar system. When the sun eventually exhausts its nuclear fuel and becomes a white dwarf, might some material remain to form new planets or moons? Pulsar planets suggest that the end of a star's life might not be the end of its planetary system. As more sensitive radio telescopes come online, astronomers may discover additional pulsar planets and gain further insights into their origins and properties. Advanced timing techniques, coupled with long-term observations, could reveal smaller, Earth-sized worlds, or even moons around these neutron stars. While these planets are unlikely candidates for life, they provide a unique perspective on the diverse paths planetary systems can take and the surprising environments where planets can be found. Pulsar planets challenge our assumptions about where planets can form, survive, and thrive. They show that even in the most extreme and seemingly inhospitable corners of the universe, planets can exist, testaments to the resilience of matter and the creativity of nature. Their discovery and continued study open a fascinating window into the complex interplay between stars, planetary systems, and the harsh realities of space. Hypercompact stellar systems, scattered throughout the universe, often hiding in the dense environments of galactic cores, are peculiar objects known as hypercompact stellar systems. These systems, small, intensely bright collections of stars, represent some of the most extreme environments in the cosmos. Their existence challenges our understanding of how stars cluster together and the forces that can shape them into such tightly bound and dynamic configurations. Hypercompact stellar systems are thought to be remnants of larger star clusters that underwent a dramatic encounter with a supermassive black hole. Imagine a cluster of stars orbiting the central black hole of a galaxy. Over time, gravitational interactions with the black hole can cause many of the cluster's stars to be ejected into space, leaving behind only the most tightly bound core of the cluster. This stripped-down core is what we observe as a hypercompact stellar system, a dense, high-energy collection of stars packed into a region far smaller than typical star clusters. One of the most striking features of hypercompact stellar systems is their size. While traditional star clusters can span hundreds of light years, hypercompact systems are often just a few light years across. Despite their small dimensions, they can contain millions of stars, all crowded into this tiny volume. This extraordinary density leads to high rates of close encounters and stellar interactions. Stars in hypercompact systems move at astonishing speeds, zipping around the cluster's center of gravity at hundreds or even thousands of kilometers per second. These extreme conditions make hypercompact stellar systems ideal environments for studying the gravitational dynamics of stars. The close proximity of so many massive objects causes the orbits of individual stars to shift rapidly over time. Stellar collisions and mergers may be more common in such systems, potentially giving rise to exotic objects like blue stragglers, stars that appear younger and more massive than their neighbors due to the accretion of material from other stars. By observing these systems, astronomers gain insights into how stars evolve under the influence of intense gravitational forces. The formation of hypercompact stellar systems is closely tied to their interaction with supermassive black holes. When a star cluster passes near a supermassive black hole, the immense gravitational pull can strip away stars from the outskirts of the cluster. Only the stars that are most tightly bound to the cluster's core remain, forming a compact remnant. In some scenarios, the core of the cluster may actually become gravitationally bound to the black hole itself, orbiting it closely and forming a stable, hypercompact configuration. This process, known as tidal stripping, effectively sculpts the cluster into a hypercompact stellar system over time. Hypercompact stellar systems are also significant for understanding the environments around supermassive black holes. They provide a window into the history of galactic centers, revealing how star clusters and black holes interact over billions of years. Their presence can offer clues about the formation of galaxies and the assembly of large-scale cosmic structures. For example, the existence of hypercompact stellar systems suggests that galactic centers are far more dynamic and violent than once thought, with frequent star ejections, intense tidal forces, and ongoing reshaping of stellar populations. One of the mysteries surrounding hypercompact stellar systems is their rarity. While many galaxies have central star clusters and supermassive black holes, not all seem to host hypercompact systems. This suggests that certain conditions are required for their formation, such as the right mass and density of the original cluster, the correct orbital trajectory around the black hole, or specific timing in the galaxy's evolutionary history. Understanding these conditions could shed light on why some galaxies produce hypercompact stellar systems, while others do not. Modern telescopes and advanced observational techniques are beginning to uncover more of these elusive objects. The Hubble Space Telescope, for example, has identified several hypercompact stellar systems in nearby galaxies. Ground-based observatories equipped with adaptive optics are also helping to resolve these tiny, dense clusters and measure their stellar motions with greater precision. Future space telescopes and next-generation instruments promise to expand the sample of known hypercompact stellar systems and provide more detailed data on their structure, composition, and dynamics. Strange quark stars. In the ever-expanding realm of exotic astrophysical objects, quark stars stand out as one of the most enigmatic possibilities. These theoretical objects, if they exist, would be even denser and more extreme than neutron stars, already among the densest known forms of matter in the universe. Quark stars may represent an intermediate stage between neutron stars and black holes, potentially providing insights into the behavior of matter under incomprehensibly high pressures and densities. Among quark stars, strange quark stars, composed largely of strange quarks, are particularly fascinating, offering a glimpse into the most fundamental building blocks of the cosmos. To understand strange quark stars, we must first consider what happens inside a neutron star. When a massive star reaches the end of its life, it can explode in a supernova, leaving behind a dense core. If that core isn't massive enough to collapse into a black hole, it becomes a neutron star, a sphere just a few miles across, but containing more mass than our Sun. The pressures inside a neutron star are so immense that protons and electrons are crushed together to form neutrons, creating a neutron-rich environment, unlike anything found on Earth. However, at the very core of a neutron star, conditions might push matter into an even more exotic state. The intense pressure and density could break down neutrons and protons into their constituent quarks, elementary particles that make up all known hadrons, particles like protons and neutrons. When this happens, the core might transition into a state of quark matter, a soup of free quarks that are no longer confined within individual neutrons. If the entire star becomes dominated by quark matter, it would no longer be a neutron star, but a quark star. Strange quark stars take this concept one step further. In addition to up and down quarks, the two lightest quarks that make up protons and neutrons, there's a third type known as the strange quark. Under extreme conditions, some of the up and down quarks in the quark matter could transform into strange quarks. This process would lower the system's energy, potentially making strange quark matter more stable than ordinary nuclear matter. A star composed largely of strange quark matter would be a strange star. What sets strange quark stars apart is their potential stability and their unique physical properties. In theory, strange quark matter could be so stable that it might persist indefinitely. If even a small amount of strange quark matter were to form, it might catalyze the conversion of surrounding neutron matter into more strange matter, turning an ordinary neutron star into a strange star. This seed conversion process could explain why strange stars, if they exist, might be relatively rare but still observable under certain conditions. The properties of strange quark stars would be extraordinarily different from those of regular neutron stars. They would be slightly smaller and denser, with a more uniform interior structure. Their surfaces might also be fundamentally different. Instead of a crust made of nuclei and electrons, a strange quark star might have a bare quark matter surface, or a thin layer of strange matter that emits radiation in unusual ways. This could lead to unique observational signatures, such as unusual pulsation patterns, distinctive X-ray or gamma-ray spectra, or atypical cooling rates. Despite their theoretical appeal, no confirmed strange quark stars have been discovered. However, certain observations have fueled speculation. For example, a few neutron stars appear to have masses, or radii, that don't neatly fit standard neutron star models. Some of these outliers might be better explained if they were strange stars. Additionally, strange quark stars could help solve puzzles related to extremely fast-spinning pulsars or stars that seem unusually cold for their age. Studying strange quark stars could open a window into fundamental physics. The behavior of quark matter and the transition between nuclear and quark phases are not well understood, as they involve conditions far beyond anything achievable in terrestrial laboratories. Quark stars might provide natural laboratories for testing theories of quantum chromodynamics, QCD, the fundamental theory that governs the interactions of quarks and gluons. By comparing theoretical models to astronomical observations, physicists could gain new insights into the strong nuclear force and the behavior of matter at the most extreme densities. Lagrange points and Trojan asteroids. In the intricate gravitational dance between two massive objects such as the Earth and the Sun, or Jupiter and the Sun, there exist special regions known as Lagrange points. These points are places in space where the gravitational forces of the two large bodies, combined with the centripetal force from their orbital motion, create a stable environment for smaller objects. As a result, these regions can trap asteroids, dust, or even artificial satellites, making them fascinating locations for both natural phenomena and human-made exploration. There are 5 Lagrange points in any two-body orbital system, designated L1 through L5. 3 of these, L1, L2, and L3, are unstable points that can hold objects temporarily, but will eventually allow them to drift away unless actively maintained. The remaining 2 points, L4 and L5, are stable regions where objects can remain for long periods without external intervention. L4 and L5 form equilateral triangles with the 2 massive bodies, lying 60 degrees ahead of and behind the smaller body's orbit. For example, in the Sun-Earth system, L4 and L5 are points in the Earth's orbital path, where the gravitational pull of the Sun and Earth balance the orbital motion, creating regions of relative stability. These stable points are particularly interesting because they naturally collect material, such as asteroids, over billions of years. In the case of the Sun-Jupiter system, these regions host groups of asteroids known as the Trojan asteroids. Named after figures from Greek mythology, these Trojans are divided into 2 camps, one at L4, leading Jupiter in its orbit, and another at L5, trailing Jupiter. Together, they form one of the largest populations of small bodies in the solar system. Their stable orbits have allowed them to remain relatively unchanged since the early days of the solar system, making them valuable time capsules of its formation. Trojan asteroids are not unique to Jupiter. Neptune, and possibly even Earth and Mars, have their own Trojans, though these populations are smaller and less well studied. The discovery of Earth's first confirmed Trojan asteroid, 2010 TK7, in the L4 point of the Earth-Sun system, demonstrated that even our own planet has stable companions sharing its orbit. These objects may offer insights into the early distribution of material in the inner solar system and the processes that led to the formation of the terrestrial planets. Lagrange points aren't just useful for understanding natural phenomena, they are also prime real estate for space exploration. The Earth-Sun L1 and L2 points, in particular, have become popular locations for scientific observatories. L1, located between Earth and the Sun, provides a continuous, unobstructed view of the Sun, making it ideal for solar observatories like the Solar and Heliospheric Observatory, SOHO. L2, on the opposite side of Earth from the Sun, offers a stable environment with minimal thermal interference, making it perfect for space telescopes like the James Webb Space Telescope. These points allow spacecraft to hover in place relative to Earth, providing stable vantage points for long-term observations. The stability of L4 and L5 points also makes them intriguing targets for future human exploration. The material collected there, such as asteroids or dust, could potentially be mined for resources, serving as stepping stones for more ambitious missions deeper into the solar system. Some have even suggested that L4 and L5 could be prime locations for large, self-sustaining space habitats, or staging areas for missions to the Moon, Mars, and beyond. In addition to their practical uses, Lagrange points and their associated objects raise fascinating scientific questions. The study of Trojan asteroids, for instance, can provide clues about how giant planets migrated early in the solar system's history. By analyzing the composition, size distribution, and orbits of these asteroids, scientists can reconstruct the movements of Jupiter and Saturn and their influence on the outer solar system. Similarly, the detection of Trojan-like objects around exoplanetary systems could offer a new window into the dynamics of distant worlds. The concept of Lagrange points also has a broader appeal, blending the fields of astrophysics, orbital mechanics, and planetary science. These points are mathematical solutions to the three-body problem, a classic challenge in physics. They reveal how even in the complex gravitational interplay of multiple celestial bodies, there exist regions of relative simplicity, places where the forces cancel out and stability emerges. This elegant balance not only explains the clustering of Trojan asteroids, but also guides the placement of cutting-edge observatories and inspires future space missions. Ring galaxies and peculiar galactic shapes. The vast cosmos is home to galaxies of every conceivable shape and size, from majestic spirals to sprawling ellipticals. Yet, among these cosmic structures, there exist rare and extraordinary formations that defy traditional classification. Ring galaxies, in particular, stand out as some of the most unusual and captivating galactic phenomena. These are galaxies shaped like colossal cosmic donuts, often with a bright, star-forming ring encircling a seemingly empty center. Beyond their striking beauty, these peculiar galactic shapes challenge our understanding of how galaxies interact, evolve, and respond to gravitational forces. Ring galaxies are thought to form primarily through galaxy collisions. When a smaller galaxy passes directly through the core of a larger disk galaxy, it sets off ripples in the larger galaxy's structure, much like a stone thrown into a still pond. These gravitational ripples compress gas and dust in the disk into a tight, circular wave that sweeps outward. As this wave propagates, it triggers an intense burst of star formation, resulting in a bright, luminous ring of young, hot stars. Over time, the inner regions of the galaxy may become depleted of gas, leaving behind a relatively empty core surrounded by the vibrant outer ring. One of the most well-known examples of a ring galaxy is the Cartwheel Galaxy. Located roughly 500 million light-years away in the constellation Sculptor, the Cartwheel is a stunning spectacle of cosmic dynamics. Its bright, clumpy ring of star formation encircles a fainter, older disk of stars, while faint spokes of material connect the inner and outer regions. The Cartwheel's unique structure suggests a recent, violent collision with a smaller galaxy, which passed through its center and created the distinctive ring. Observing the Cartwheel and similar galaxies helps astronomers reconstruct these past interactions and understand the conditions that lead to ring formation. Not all ring galaxies are created through collisions, however. Some may result from internal processes, such as bar-driven resonance patterns in disk galaxies. In barred spiral galaxies, a central bar structure can channel gas towards certain resonances, creating rings at specific distances from the galactic center. These resonance rings tend to be more symmetrical and less dramatic than their collision-induced counterparts, but they still stand out as distinctive features that reveal the underlying dynamics of the galaxy's rotation and structure. Beyond traditional ring galaxies, astronomers have also identified other peculiar galactic shapes that defy conventional norms. Polar ring galaxies, for example, feature a disk of stars and gas aligned in one plane, with a separate ring of material orbiting in a perpendicular plane. These rings are thought to form when a galaxy accretes material from a nearby companion or captures gas from intergalactic space. The resulting perpendicular ring creates a strikingly unusual appearance and provides clues about how galaxies acquire new material and grow over time. Other peculiar galactic shapes include warped and twisted disks, galaxies with off-center nuclei, and structures that appear to be midway through a merger or in the aftermath of a recent collision. These unusual formations often occur in dense galactic environments, such as galaxy clusters or groups, where gravitational interactions are frequent and intense. The tidal forces exerted by close encounters can distort a galaxy's shape, creating elongated tails, bridges of material between galaxies, or even completely reshaping a galaxy's structure into something unrecognizable from its original form. Studying these peculiar galactic shapes, including ring galaxies, offers valuable insights into the complex interplay of gravity, gas dynamics, and star formation. By analyzing their properties, astronomers can learn about the distribution of dark matter within galaxies, the nature of their central black holes, and the processes that drive starbursts. Furthermore, these studies help refine computer simulations of galaxy evolution, providing a better understanding of how galaxies grow and change over billions of years. The rarity of ring galaxies and other unusual shapes makes them particularly intriguing. While most galaxies settle into more familiar forms, spirals, ellipticals, and irregulars, these peculiar configurations demonstrate the diversity and dynamism of the universe. They remind us that galaxies are not static objects, but rather evolving systems shaped by their environments, their histories, and their interactions with neighbors. Observing these unique structures challenges astronomers to think beyond standard models and explore the wide range of possibilities that nature has to offer. The cold spot in the cosmic microwave background. The cosmic microwave background, CMB, is a faint glow of radiation that fills the entire universe, a relic from the Big Bang that has traveled for over 13.8 billion years. Discovered in the mid-20th century, the CMB provides a snapshot of the infant universe when it was just 380,000 years old. Across this ancient radiation field, the temperature is remarkably uniform, differing by only a few hundred microkelvin in most places. But among the subtle variations, there's one anomaly that has puzzled scientists for decades: the cold spot. First detected by NASA's Wilkinson Microwave Anisotropy Probe, WMAP, and later confirmed by the European Space Agency's Planck satellite, the cold spot is an unusually large, low-temperature region in the CMB. Located in the southern hemisphere of the sky, this area is significantly colder than the surrounding regions. It stretches roughly 5 degrees across the sky, an enormous size in cosmological terms, and stands out as one of the most prominent features in the CMB. What makes the cold spot so intriguing is that it doesn't fit neatly into the standard cosmological model. The CMB's variations are typically explained by quantum fluctuations in the early universe, stretched out by cosmic inflation. These fluctuations should create a pattern of hot and cold spots that follow a predictable statistical distribution. The cold spot, however, is both larger and colder than the model predicts, suggesting that something unusual might have occurred in this part of the universe's history. Several hypotheses have been proposed to explain the cold spot. One idea is that it's simply a statistical fluke, a rare but natural occurrence that doesn't require any new physics. In this scenario, the cold spot would be an extreme outlier, but still consistent with the known laws of physics. However, the size and severity of the cold spot make this explanation less likely, prompting scientists to explore other possibilities. Another hypothesis involves a massive supervoid in the universe. A supervoid is a vast region of space that contains far fewer galaxies, stars, and matter than average. If a supervoid lies in the direction of the cold spot, it could affect the CMB photons as they pass through it. Known as the integrated Sachs-Wolf effect, This phenomenon occurs when photons lose energy as they climb out of the gravitational well of the void. The result would be a cooler than expected patch of the CMB. Indeed, surveys of the large-scale structure of the universe have hinted at the presence of a supervoid in the vicinity of the cold spot, though its exact properties and influence remain uncertain. Beyond supervoids, some more exotic explanations have been considered. One possibility is that the cold spot represents evidence of non-standard cosmology, such as variations in the fundamental constants of nature or early universe physics that go beyond the simple inflationary model. Another tantalizing idea is that the cold spot might be a hint of a multiverse, where our universe collided with another bubble universe during inflation. Such a collision could leave a distinctive imprint on the CMB, potentially manifesting as a cold, circular region. While these speculative ideas are intriguing, they remain unproven. The challenge lies in obtaining enough data to distinguish between competing explanations. Current and upcoming surveys of galaxies, cosmic voids, and other large-scale structures aim to provide more detailed maps of the universe's matter distribution. These data could confirm or refute the supervoid hypothesis, and may also reveal new clues about the physics underlying the cold spot. Regardless of its origin, the cold spot is a reminder of how much we still have to learn about the universe. It highlights the complexity of the early cosmos and the interplay of quantum fluctuations, inflation, and gravitational effects that shape the largest structures we see today. It also underscores the importance of precision measurements and theoretical creativity in cosmology as scientists seek to explain not just the typical patterns of the CMB, but also its rare anomalies. In the end, the cold spot represents both a mystery and an opportunity. It may hold the key to new discoveries about the universe's beginnings, the nature of dark energy, or the possibility of other universes. Or it may simply remind us that even the most elegant models sometimes produce surprises. Either way, the cold spot serves as a testament to the richness of the cosmic tapestry and the enduring quest to understand our place within it. The mysterious Tabby's star in the vast night sky, filled with countless stars shining steadily or pulsing rhythmically, a particular celestial object known as Tabby's star has drawn the fascination of astronomers, researchers, and the general public alike. Officially designated KIC 8462852, this star captured attention because of its highly unusual behavior, brightness fluctuations so erratic and pronounced that they defy traditional explanations. Since its discovery, Tabby's star has sparked intense debate and speculation, becoming one of the most enigmatic stars observed by modern science. The star was first noted during the Kepler Space Telescope's mission, which was designed to hunt for exoplanets by detecting dips in starlight caused by planets passing or transiting in front of their host stars. Most stars observed by Kepler displayed regular, periodic dimming patterns, consistent with planets orbiting at predictable intervals. Tabby's star, however, exhibited something entirely different. Instead of a smooth, recurring pattern, its brightness dropped dramatically at irregular intervals and by varying amounts, sometimes as much as 22%, a far larger decrease than any known exoplanet could cause. Initially, scientists considered the possibility of a planetary system with unusual dynamics, but the light curve didn't match the profiles expected from exoplanet transits. The dips were too deep, too erratic, and lacked the predictable periodicity that would indicate a planet's orbit. This left researchers searching for other explanations, many of which range from natural phenomena to more speculative ideas. One leading hypothesis proposed that a swarm of comets, or fragments, from a disrupted planet might be orbiting the star, occasionally blocking its light in an irregular pattern. Such debris could account for some of the variability, though it would require an enormous amount of material and a precise set of circumstances to produce the observed light curve. While plausible, this explanation didn't fully satisfy all the data, especially the long-term fading trend that had also been noted in archival records. Another natural explanation considered the possibility of a massive cloud of interstellar dust passing between Earth and Tabby's star. This dust could scatter or absorb certain wavelengths of light, causing the star's apparent brightness to change over time. However, follow-up observations across multiple wavelengths showed that the dips were not consistent with simple dust absorption, as the star's color didn't shift in the way expected if dust were the primary culprit. As the more conventional theories struggled to fully account for the observations, a more speculative idea gained public and media attention: the possibility of an alien megastructure. Some researchers speculated that a highly advanced extraterrestrial civilization could have built a Dyson swarm, a series of large structures orbiting their star to capture its energy. Such a megastructure, if incomplete or irregular, might create the odd light patterns seen around Tabby's star. While this idea was always considered a last resort hypothesis, it highlighted just how unusual the star's behavior appeared and how few explanations seemed to fit. Over time, additional observations and studies have helped narrow down the potential causes, though the mystery is not entirely solved. Extensive monitoring by ground-based telescopes and space observatories has provided a more detailed view of the star's behavior. Researchers have analyzed the dips in starlight at different wavelengths, tracked long-term changes in brightness, and compared Tabby's star to similar stars in the vicinity. While no single explanation has definitively emerged, the evidence increasingly points to complex, natural phenomena rather than artificial structures. One promising avenue involves a combination of dust and circumstellar material, potentially remnants from a past planetary disruption or ongoing activity in the star's vicinity. Observations have revealed that the star's dimming is more pronounced at certain wavelengths, consistent with fine particles or gas clouds partially obscuring the light. This doesn't completely solve the puzzle, but it suggests that multiple overlapping factors, rather than a single dramatic event, may be responsible. Tabby's star has not only deepened our understanding of stellar variability, but it has also inspired innovative approaches to data analysis and public engagement. Crowdsourced projects, amateur astronomers, and professional collaborations have all contributed to studying this unusual object. The mystery has fueled broader discussions about the limits of current astrophysical models, the role of unexpected phenomena in advancing science, and the importance of keeping an open mind when exploring the unknown.